Okay. 2 minutes. I'm trying to like clear my throat here.
Yeah, I know. It's great. Our mics are on.
Yeah.
Hear it.
Oh, I see. We'll probably get started in like 2 minutes. You can keep talking amongst yourselves.
Please keep chatting. Make friends.
All right, check. Hello. Cool. Well, thank you everyone for being here. We really appreciate it. I'm excited to see a bunch of really familiar faces and some new faces as well. I'm Joey. I lead the Discover team, and I'm here with Kent.
I'm Kent. I work across Discover and social and various other areas at Fortnite. And this year, Joey is going to be taking the lead on the presentation, which is a great opportunity for him. And I'll be here talking a bit as well. But we're so excited to hear from what you have to say.
Yeah, and unfortunately, I woke up 2 days ago and my voice was gone. So I will be drinking tea while I go, and hopefully it's not too scratchy and too unbearable. But yeah, only like 25 minutes, and then we'll probably spend the rest doing like a Q&A at the end. So let's get started. Our talk, again, is called Finding Success in Discover. Quick table of contents, some of the stuff we're going to talk through. This might look pretty familiar. Key metrics, so introducing Discover score, new content testing and talking about sophistication, search, personalization, and for you. We have some experimental changes with the Discover UI, and then some just like adjacent, a little bit more miscellaneous features related to like matchmaking, favorite a creator, stuff like that. The other thing that I just want to say up front before we jump into all of the nitty-gritty details is like a lot of this is subject to change. As you may have noticed, like over the past couple of weeks, we've had a pretty major effort towards like improving transparency across the ecosystem. So as we make those changes, we want to also be communicating that with you, especially when there are substantial changes to Discover algorithms, things like that. Like we want to use the new Discover documentation as like the source of truth for what's happening, and then we'll try to accompany that with different messaging on socials of like, hey, we've made some updates. These are the things that we're changing. This is going to be a learning process, like a process, but we're really excited, and we think that this is the right direction for us to keep moving in. So let's get started. This might look very familiar if you were here last year. So I'm kind of starting on a very similar slide of like how Discover works, engagement, attraction, and satisfaction. So we're trying to go kind of like a layer deeper than we did in the previous session. So again, attraction is just how well your island converts impressions into sustained engagement. Again, sustained engagement is players playing consistently after they click into an experience and not just joining and then leaving. And then some of the metrics in particular that we look at are things like clicks per impression, minutes per impression, and then percentage of players that are leaving in 2, 5, 10 minutes into that experience. And when we highlight all of the metrics here, these are used in various parts of Discover, so they could be used in sorts, they have filters, or they could be used in parts of like For You or Discover Score, which Kent will talk about in a second. We have engagement, so keeping players invested and interested in your island once they've joined, and then players coming back to the island. So again, the metrics here are like minutes per player, D1 and D7 retention, which we got a question before about exactly how that works. D1 retention is just all of the players on this first day who come back the next day. So it isn't necessarily like new to Fortnite or new to your game necessarily. It is just players who came the next day. And then D7 retention is players who came back 7 days later. Exactly 7 days later. So it is not people who played within that 7-day window. It is they played on day 1 and then they played on day 7. Number of unique players over the last 96 hours, and then social party time spent. We use 96 hours here for a couple of pretty specific reasons. One, it sort of like inherently bakes in a little bit of retention into a lot of the different metrics. We get a very common question that we get is like, hey, if someone plays my game multiple sessions throughout a day, how is that counted in Discover? And so what we do with the 96-hour is we aggregate all of those sessions together, and that combined becomes the engagement that you get for that given player. So it's okay that a player plays for 5 minutes, drops out, and then comes back and plays again, and then they come back again the next day. Those are all really great things, and we want to see players sort of jumping in and out and returning to their favorite experiences. I want to take a minute to also talk about idle time. So this came up on Friday as we released some of the documentation. Discover does not count engagement while a player is idle. This has been the case since the end of 2023. If a player hasn't registered an input for 60 seconds, they are considered idle. And if they've registered any input at all, they count as active. And so any input includes like moving the camera, any keyboard press, any controller press. As a way to sort of visualize this, I grabbed a few of the top sort of genres across the ecosystem and just looked at average idle rates for those different genres across all islands within that genre. And so this was the rough breakdown. All of these fall like well within the like filters that we are using for idle time across our different Discover rows. And so some of that is outlined in the documentation.
And I think the flag to offer here, and there's a lot of discussion about idle minutes and idle time, is we want Fortnite to be the best place to go to play games with your friends. And when you are sitting away from your console for hours or lots of time, that is kind of not playing games with your friends. That is actually something else. And so while we don't want to overly punish games, there's, tycoons and these things, these are loops that are well established. We don't want to create huge incentives to make games where you just arrive and then just leave. And so just kind of flagging that. Another question as well from kind of that Friday live stream was how this works in spectating. You can still be flagged as idle in the lobby while spectating or while playing a game. And again, it's a very strict definition. If you press anything, you are no longer idle for that entire minute. So I could press one button, wait 50 seconds. If it's still in that minute, I'm still active, right? We haven't dinged it. It's just a matter of basically people going AFK for really extended periods of time where you can imagine someone just sitting in an island for just hours and hours. And look forward to Q&A on this because I know it's a hot topic.
Sweet. We'll keep rolling. Satisfaction. So how satisfied players are with your experience that they just had on your island. Do they favorite and recommend the island? Again, the metrics here I think are pretty straightforward, but we've given you sort of fun scores, satisfaction scores, number of favorites, and recommendations. Cool, now so Kent is gonna kind of talk about how all of these come together into Discover Score.
Yep, because we talk a lot about how attraction, engagement, satisfaction, these are the pillars to success in Discover. But how we actually operationalize that has been an open question that people might not necessarily know. And so Discover Score is our attempt that we launched earlier this year to basically try to combine all these metrics into one number to kind of understand your broad appeal within Discover to the audiences we're showing you to. And you can see them there. We're looking at unique users over 4 days, minutes per player over 4 days, click-through rate, and then the survey fun score, the people reporting they had a fun or good time within your match. If you go to the next slide, again, there were some great questions after the documentation came out over like, what is the literal math happening here? And it's nothing too crazy. If you go on Wikipedia, this is called a standard score or a Z-score. Essentially, we have to compare numbers that are quite different from each other. A click-through rate is a percentage. It's between 0 and 1. unique players can go up to like 50 million, right? And so how do I have a number that's like 0.2 carry the same weight as a number that's 50 million? And that's where a standard score comes in, where first we apply a logarithm to make sure that outliers, tails, are not driving the score too much. So maybe I'm really spiky on one metric and then everything else is pretty bland. We don't want to necessarily over-index that you're really good at just one thing. So that's where the logarithm comes in to kind of compress this distribution down. And then from there, for each metric, we look at the average for that metric, and then the distribution, aka the standard deviation, to understand, so say the average click-through rate is 5%, and the standard deviation is also 5%. So if you have a click-through rate of 10%, that's +1 score. And if you have a click-through rate of 0%, that's -1 score. And all this math can be done on a basic calculator. It takes like a millisecond to run. It's very basic. But for every island, across all these metrics, multiple times a day, we are recomputing this Discover score as you gain exposure or data rolls out of that 96-hour rolling window. And for us, this allows us to take a really holistic view of island quality and not trying to over-index on any one of the metrics, ensuring they're all being served in context of each other. And right now, this is mostly used to drive the For You row in our recommendation systems. But going forward, we want to find ways to, one, expose it to you all so you can understand your own Discover scores, but then also integrate it deeper into other parts of Discover as we gain faith. This is something that is like actually identifying awesome content. So happy to walk through some boring math with you all, and Joey's going to keep going.
Yeah, the other thing that I would just add on is I think one of the really powerful things about this score is hopefully, as you make changes and you make your islands better and you increase your minutes per player and you increase how much fun players are having, your score pretty immediately reflects that. It starts to go up. You start getting shown more in recommendations. You start getting shown more in other rows. And you kind of create this really solid feedback loop. I think that's why it's really important that we provide a lot of this data back to you in Creator Analytics or via the data API. I think I didn't say it at the beginning, but like, we introduced a ton of new stuff, I would say, in the last like 7 days. We're kind of still catching up and being like, okay, well, a bunch of the things we added, we don't actually tell you yet. Like, we need to tell you those things, and so all of that is like conversations that are happening now. We should be adding those things soon. Oh, actually, do you want to keep going on new content testing?
Yeah, absolutely. And so we're about to introduce a second score, similar to Discover score, on the next slide, that's related to new content testing, where when we receive new and updated islands, we make an effort to get as many of those islands as we can to 50,000 impressions in a 4 to 7 day window after their update. And we don't include impressions from sources that you're kind of driving yourself, things like search, recently played, library, as part of this test. All other impressions in Discover, so if you make it into For You or go somewhere else, that still would count as a test. It doesn't have to be from new and updated, but we're trying to focus on basically impressions that Discover is handing you, not things that you have earned yourself, like search or in that vein. And when we think about prioritizing new islands, again, this was in the documentation and there's a deeper write-up on it there, we're using something called sophistication score, which is doing the identical statistical approach, that standard score we talked about 2 slides ago. But instead of looking at the island's engagement and its players, we're looking at what is actually happening on the island through the development process. How much effort was spent building this island? What devices, animations, sequencers, many, many other things are in there? How much verse code is being used and how? And many more metrics as well. And again, we're doing the same statistical methods we did to Discover score to prevent outliers from skewing any particular number particularly high. So if I have 1 billion verse lines, that shouldn't just jump you to the top, so to speak. And again, just calling out as well, we get a lot of questions on this. Reusing verse code, devices, all that stuff from existing islands, things you've already made, is a totally fine development practice. And the key thing we're trying to avoid, and as we see in our ecosystem a good bit, is people just trying to duplicate the same island and submitting it over and over and over. And essentially, we're looking for effort and evidence of using advanced systems on your island. For updated islands, actually, if you go back, sorry, Joey.
Trying.
For updated islands, we're using a slightly different prioritization, which is based on development effort over the last 30 days. For this, we want to make sure that you're making a meaningful change or a meaningful attempt to change the island to something else, not necessarily just tweaking a thumbnail or just pushing a new update. We're trying to understand, is this a substantial update? And so when we try to prioritize our updated islands, this is how we're doing so. So this is an exciting one, and it's not yet in documentation, and it's not yet live, hence the coming soon at the top. But this is something that we're really excited about and has been one of the top requests from creators we get each and every day, which is basically looking for games that are newly published and coming in that are very, very similar to an existing game in our ecosystem. And so starting later this summer, starting particularly for brand new islands, in the publishing flow, we're going to be looking at games that have exact matches of a title or a thumbnail already in the ecosystem, and we're going to block publishing at that moment. And you're going to get you can change the title, you're going to be aware right there that this is happening. There won't be a mystery there, because we don't want people creating content trying to pose as content that's not theirs. And now the natural step after you block publishing of an exact match is I'm going to make it a near exact match. And that's where Discover downranking comes in, where maps that have very high overlap scores with other games on thumbnails and titles could receive a Discover downranking. And again, every map that would receive this is going to receive a warning right there in the creator portal that this could happen right as you type in title or upload your thumbnail. So you won't be guessing. But downranked islands will not be eligible for a lot of our more kind of like organic viral rows. Things like the new and updated row, for you, trending, and text search. Meaning if I type in a generic term, call it red versus blue, if I have been identified as being very, very similar to an existing game, I will not be eligible to show up if I've been flagged that way. These islands will still remain eligible for things like recently played, favorites, creator pages, if I type in that exact island code. But this is kind of a baby step towards trying to disincentivize creating exact clone copies of existing games in the ecosystem. And if you go to the next slide, again, we don't have a launch date for this yet, but it's such a hot topic that we wanted to bring it to you nice and early. We want to ensure there's appropriate carve-outs. You as a creator who's made an island should be able to publish an island with a very similar name to your existing island. Call it Havoc Hotel 1 and Havoc Hotel 2. That should be totally fine. And we want to start enforcement on brand new islands. And we want to potentially expand from there depending on how that goes. But we don't want to try to create massive disruption to existing games that already have an audience that are doing their thing. We want to start by the inflow of content that looks to be extremely similar to existing games. And finally, as is the theme of this week, we want to become ever more transparent with these things where you don't have to guess, you can just know. And so before this is launched, Discover documentation is going to update with much deeper specifics on how this was specifically implemented and what it means for your islands and your publishes going forward.
Great. Excuse me. So I want to talk a little bit about search and for you. We made some changes to search recently. And so now search is using a kind of hybrid approach combining two different algorithms, keyword matching and semantic search. And this is something that we're going to be kind of continuing to experiment with over the next couple of months. Keyword matching basically just returns islands that contain sort of exact text keyword matches for the user's query. Whereas semantic search looks for islands that are semantically similar. And so sort of what that means is islands that have a similar sort of theme or show up together. So like if I search for scary, like horror islands might show up, even though they don't necessarily match one-to-one on the text. The current implementation of this is actually like pretty tame, I would say. We're not trying to go over aggressive on semantic search just yet. And we want to really make sure we're indexing on keyword matching and that players or the content is showing up that players are searching for. But it's something that we want to keep experimenting with over time. We want to encourage players to search for the types of games that they're interested in playing rather than necessarily knowing, oh, I know exactly the title. But both should work. And so that will continue to sort of be the standard we hold ourselves to, is that like there should never be a case where if I type in my game's title, the game doesn't get returned in search. But like we're going to kind of experiment with different versions, different weightings with these different variables, and we're going to add more variables over time. We're also going to be trialing two different sort of UI, UX versions of search that you're going to see over the coming months. We have some slides later in the deck where we'll go over that. Okay, I also wanted to take a couple minutes to go through how For You works across Discover. Again, a lot of this is in the Discover documentation, so I'll try not to spend too much time getting into the details. But I do think it's really interesting, and this is an area that we want to continue to lean into, just because of how effective we think it is at both like surfacing a variety of content and also surfacing the content that players are interested in back to them. So we start with like the pool of possible recommendations. So we grab top islands across the ecosystem using that same Discover score that we talked about. Roughly, this is about 2,000 islands at any given point. But again, I mentioned that Discover score is kind of always changing. And so like the thresholds for what islands are included or excluded can also shift a little bit. The way we identify top islands is we use the different categories that we've defined across Discover. And we try to pull top islands from each category so that we ensure there's a certain amount of like variety across all of the different content that qualifies. And it's not just overly saturated from one specific genre. And then the other nice note about recommendations is that these are all generally real time. They update after each game that's played. And then that helps drive rotation and sort of variety of play for players. So that's the pool of content. The next piece of this puzzle, kind of, is island representation. So this is how we understand an island to work and what islands are maybe similar to it. Essentially, what this boils down to is we have a bunch of different input features, like the title, description, thumbnail, as well as like telemetry. That includes things like used in the sophistication score, so devices, animations, and stuff like that, as well as weapons, builds, vehicles, driving, a bunch of different variables about how players are engaging with content in the island. We sort of mush all of that together into a single point in space, and it allows us to plot islands, kind of like you see, around a 3D space with islands that are similar to them. And so this gives us a really good understanding of like the ecosystem, what content is pretty similar to each other, and what content is pretty different. So once we have an understanding of the islands, we also then can build out an understanding of players. And so we can look at a player's history, we can look at their favorited categories, their favorited islands and creators, and we can do a similar thing and plot them in space as well, based on that play history. And players are different where they might have like a couple of different points in space, right? Like you might play one type of genre and a completely different genre, and that's okay. And so you'll have two different spots. But if you also only play one genre, then you'll just have one spot. And so we kind of match these together, and then we're able to say, hey, like you exist in space here, and there are a bunch of islands around you based on that type of similar content, and we can serve that up to you. This also works really well for new players who are coming into the ecosystem, and they sort of favorite whatever categories they're interested in playing. It allows us to pretty immediately return recommendations back to them based on whatever they selected, and then as they play content and they fill out their play history, those recommendations will slowly adjust over time. So the very last piece of this is just sort of surfacing different model types, and that's just different ways that we can combine island and player representations. And so one might be like, hey, we're going to give you like 4 islands that are really similar to something that you just played, or to where we think that you exist within like this galaxy. Another might be we look at players' sequencing of play, and we see that, hey, people who played this island played these 3 islands kind of in sequence afterward, and we surface those islands back to you. And so we're sort of constantly experimenting and testing different versions of these models, but they're all based on that same sort of embeddings framework of how we understand an island and a player. And then there's just different ways that we can sort of return the content back to you. We can shuffle it, we can not shuffle it, and so there's just sort of constant experimentation happening here to generally try to maximize, or return the right content to the right players.
And ideally, it should be somewhat intuitive, right? Where if you look at that sequencer model, if I play a 1v1 for 15 minutes, when we look at our players, that's a pretty likely behavior. You might be warming up to play ranked. And so when you exit that 1v1, it might not make sense to serve you 12 more 1v1s. It might make sense to serve you the thing you were warming up for. In the inverse, if I'm a huge variety player and I just love party royales and tycoons and all that stuff, when I leave a tycoon, it's going to make sense for me to serve you other tycoons to make sure you can find other stuff to play. And so as we think about players intuitively, hopefully you can think about player journeys in your life and your friend's life and see how this might manifest to different types of recommendations and how that might be served.
Cool. One last thing that we want to add, we talked about this earlier this year, I think, is just having explicit negative signal from players. So this is, hey, I played an experience and I really didn't like it, or I see this thing being recommended to me and I'm really not interested in it. We can use this as explicit signal to say, hey, okay, we shouldn't recommend this thing again. And also, we can now adjust where you are in that galaxy and say, let's move you away from content that you're telling us that you're not interested in. So this should be going live. I don't want to give a specific date. It should be very soon.
Imminent.
Yeah, in the next like 1 to 2 patches, I think. But it's got, like, we've had a couple issues with like client bugs, and so it's pushed it back. Cool. The last little bit here for me is I want to talk through some of the Discover UI changes. I wanted to pause here just for a second. Like, we want to be more methodical in the way that we're introducing changes to the Discover UI. And so a lot of these changes are going to be different A/B tests or versions of A/B tests going forward so that we can understand how does this actually change the way that players interact with content, with Discover. And so you might see these changes, but you might not, or you might see it talked about, and I don't want anyone to be confused by that. That's just us testing different versions to kind of understand what works and what's not working. So this is one of the first changes. we are considering kind of putting search more directly in Discover. So the view here is you were on the home bar, you scrolled down, this is sort of the very top of your Discover now. So you can search for content right away. There's another version of this where we could default you right to the first tile on For You, rather than defaulting you to the search bar. And then you can kind of continue your Discover experience normally. We're also considering adding these tabs on the right side that allow you to filter for specific content. And also sort of reinforces that creator favorite / follower relationship. Some of the language here might change. We're still sort of figuring out whether favorites or following really make sense. But this is kind of the general idea. And so on the tabs, if you were to navigate over to the following tab, you could see the different creators that you follow. You could see new releases from those creators. You could see what's recently updated. Again, the ordering and things might change here, but the idea is to sort of reestablish or make a clearer way for players to identify, hey, I care about these creators. I've played a lot of their content. I want to see updates from them, and this is a faster way for me to go and get those updates. Cool. I think I'm going to hand it to Kent now to talk through some of those miscellaneous other things.
You say miscellaneous, I say the future. On that note of elevating following, we have seen just tremendous growth in favorite a creator this year. This is a cumulative sum of number of kind of player-creator relationships we have. Since I pulled this data, we're already up to like 46 million. We're on track to have over 100 million towards the end of this year. And what's even more exciting, as Sax mentioned on stage, we have 6 over 1 million. But what gets me really jazzed is we have 112 over 50,000 and over 450 over 10,000 favorites. And what we're seeing is that you don't need a ton of favorites to be able to kind of have a fully self-contained content testing loop for creators. One anecdote, and I have to anonymize it, but they're a creator that some folks here would know. They had about 20,000 favorites, and they published a new game, and we saw this game hit 500 CCU, and it was instant. It was like, oh, this is great. And we checked Discover just obsessively, and we're saying, how did this game get 500 CCU? It hasn't been in a testing row, it hasn't been in For You. And it turned out it was just in new and updated from favorited creators, and it had an over 60% click-through rate from their core fan base, meaning they were able to turn 15 to 20,000 favorites into 500 concurrent users within 2 hours of launch. And for us, this was just a magical moment of like, holy cow, these creators are able to like generate a following and a fandom that is obsessed with their content. 60% click-through rate is like, I'm here for this, I love this. And so for us, those UI changes are in service of kind of enabling that dream. If you read the Discover Vision document, we talked about sustainable success as a core goal, and that word sustainable is key. And we think this favorite graph is a key part to being able to, one, like, as you have success, to create almost like a nest egg or create like long-term value and following from the success you've had on platform. So we're super excited to invest in this more going forward. The other thing we're super jazzed about is the continued rise of text chat usage. Fortnite's very seasonal. December is a huge moment for us, and then spring tends to be a little bit of a light decline. And so even though CCU's down pretty significantly since text chat launch, we are still breaking records every week for the amount of text chat messages sent every week in UEFN islands. Again, since I pulled this data, we broke it again on Saturday, which is awesome. We're seeing 30 million messages a week sent in your games, and we think this is a key part of becoming more of a social interaction place, an ecosystem where people are making friends and hanging out with their friends. And when we look at the islands that are driving it as well, it's some of these awesome social variety games where people are chatting with each other and making new friends. We just released Bubble Chat in UEFN, and we know there's some bugs there, and hopefully those are going to be ironed out here pretty quickly. But we're super excited for, this chart I'm showing is before we had Bubble Chat. I dream of what it would look like after Bubble Chat as players are able to see chat more easily, more natively, all that great stuff. So we're really excited about that. And Joey has a couple things he's excited about.
I do. And I apologize. This will be the last couple of things, and we'll make sure we have time for Q&A. Wanted to give an update on Discover Quests in XP. So we recently launched Discover Category Quests. So these are weekly quests in Discover for all players where they can sort of navigate to specific categories. And the quests are just earn XP within those categories. This is a part of a larger effort for us to try to bring kind of creative quests up to a level more similar to first party and BR. And so this is a baby step in that direction, but we're really pushing while we're working on a lot of sort of more core infrastructure improvements to quests and XP. So hopefully by the end of this year, we've also been able to deliver sort of like better bad actor handling and detection of people who are abusing the XP system. We're upgrading the XP system for better stability between releases because we know that that's been an issue. And then just trying to generally improve XP parity between different creative islands. So more to come here, a lot of like infrastructure level stuff for right now, and then hopefully some more exciting stuff next year.
The root of a lot of those challenges was that rather than one single XP system, we had 5 or 6 that are working together trying to create one story, and that makes it incredibly hard to understand what's happening and also manage and maintain it. And as part of this process, we have been able to create one unified system, which is going to allow all the things Joey's talking about that we're really quite excited about.
I also wanted to take a moment to talk about matchmaking. So we recently shipped new custom matchmaking settings for creators. And so this allows creators to define basically how long of a queue time they want to wait, and then ideal match start sizes based on those queue times. So essentially you can say, hey, I want my main phase to be 30 seconds, and I want to really ideally hit 20 players in a lobby in those 30 seconds. You can extend beyond that, or you can just say, okay, and if I don't hit it after that point, just start the match with whoever you have and let's get going. So the idea here is basically like empower creators to kind of own these decisions for their game experiences because every game is going to be really different. If I'm a 1v1, I have very different matchmaking needs than if I'm a ballistic 5v5. And so the goal here is also to provide the analytics so that you can understand like when you make these changes, what actually changes for players for like your average queue time, and then like the really high and low cases of like 95th percentile, someone who was really unlucky, middle of the night in a different region, like what were they hitting? So hopefully, you can start playing around with some of these settings and adjusting your queue times. And this is all in service of a larger goal of like having fuller games and fuller lobbies. When you start the game. And so rather than starting and kind of hoping that people backfill in, and then maybe I get a full game, you can kind of do a lot of that up front, the heavy lifting on the matchmaking side, pull all of those players in, and then start with 20 players, or however many it is for your given game. A couple things that are coming soon. One, we're going to add options for skill-based matchmaking for creators. So this is going to start as a really simple checkbox where creators can just opt into skill-based matchmaking, but it's something that we want to expand on in the future. There's like larger matchmaking changes going on where we're going to be able to provide a lot more custom options for creators over time. But that's stuff for later this year, and so I don't want to commit to a specific time yet. And then the other one that we're thinking about, especially a lot recently, is sort of improved input-focused matchmaking, especially for creative islands. And so figuring out how we could deliver that in combination with some of these other features. So you can say, hey, I want to match players together based on their input type, as opposed to, for a lot, like the default for a lot of experiences is you wait 5 seconds, whoever's in queue, throw them all into game, they play together. Certain input types might be super disadvantaged compared to other ones, and that's not super fun for anyone. Cool, and I think that is all we have in terms of slides. We know that these sessions are always super valuable for Q&A, and so we wanted to try to reserve as much time as we could for that. So there's a mic here at the front, and if you would like to ask questions, please come up, and we can try to talk through them, and I am going to take a small break.
Thank you.
Yeah.
Hey everybody, how's it going? Yes, we're in Orlando. Amazing time to be here. This is the best time of year to be in Orlando. So hopefully everybody got to the keynote today. Everybody get a chance to check that out. It's exciting stuff, right? There's so much cool things happening with Epic, and we're really happy that you all are here at Unreal Fest with us to experience all the wonderful things we have going, and hoping the sessions are going well for you all and you're enjoying everything. Make sure you go to the party. The party's really, really going to be a good one. They always blow them out. I'm going to be spending the next 45 minutes or so talking to you about some of the things that are new in 5.6. So these are kind of the key features and benefits. It's different than what you saw in the keynote for the majority of it. A lot of that was very tech presentation. That CDPR project is ridiculously cool. We will be covering some of that in this presentation with different assets, but those concepts will be talked about briefly. And yeah, we'll spend most of the time running through it. We're not going to have much time for Q&A probably at the end. If you guys want to hear more or talk to us more, down in the expo, myself and some of the other Epic employees are down there, and we're always happy to talk to you. This project is loaded up on the UE demo machine, so if you want to come by and poke around and kick the tires a bit, feel free to come talk to us. So the things that we're going to be talking about today are performance, authoring, animation, so a bunch of usability, a bunch of workflow stuff, and just the overall arching message around 5.6 is it's kind of this message of maturity, right? Like a lot of the things that we've been doing with the tools have been to make them both faster, but also more productive from an art production standpoint. So a lot of the work that's gone into the animation system specifically is really geared around getting people to work very, very quickly inside of the engine. And of course, we're always striving to improve the developer iteration process, and there's lots of fun things that are, not the best demo things, but things that are definitely worth mentioning, and we'll kind of cover that off with a slide, a catch-all slide at the end. So the first thing that we're going to be talking about is performance, and this is something that we've been investing heavily in the engine. Since UE5 has come out, every release we basically improve it and try to make it faster, better algorithms, better use of resources on your computer, and 5.6 is kind of consistent along that theme. We've done a lot of really great things to improve hardware ray tracing. Tons and tons of work have gone into that to make it performant, and we're really striving to get to this 60 FPS as a default setting, on like a PS5, which is what that silver demo was running on. That wasn't a PS5 Pro, that was a standard PS5 that they were running that insanely large open world in and hitting 60 FPS. So a lot of the underlying architectural work that's been going into their last few releases really comes to an explanation point with 5.6. It's much, much faster when it comes to hardware ray tracing. So things like Lumen and all that just start to look really, really great. So let's jump over, and we're going to talk about device profiles. It's easy to profile to your devices now. It's, again, this developer process and iteration is getting more and more refined and smooth. So let's just jump over to Unreal, and I'll show you the scene I've been working on. So the scene is it's actually based in City Sample, right? So if I zoom up here and look at this guy, oops, let's jump back into my Unreal and just kind of fly up. So it is a city sample, and basically what I did is I grabbed like this kind of T-shape, these first two blocks in this outer street, and I just started smashing in a bunch of assets that I got off of Fab. So all this geometry and all these assets came off of Fab, and it's just this really heavy, dense, intense scene. And the thing that's really interesting about this is City Sample's underneath this, right? So we've taken what we've done in UE5 back in the day, and we've layered on top of it a much more dense meshes, as well as a lot more stacked translucency and things like that. So we were doing like those cube maps in the windows and things like that in the City Sample because that's what we could do at that time to run at that scale. Now here we are at 5.6, and we have the ability to do things a little bit more realistically. Like I've got tons and tons of geometry stacked behind these stores and things like that, and it just works, which is really, really pretty cool. Also in this scene, I've got two different lighting models. Right now, we're looking at the night lighting model, and obviously I'm using Mega Lights to do this. This scene has about 700 different ray trace lights inside of it, and there's a lot of emissive materials inside of here. Wherever there's the emissive signs, or not everywhere, because I didn't have enough time to place a million lights, but where a lot of those emissive signs are, I've gone through and I've put either area lights or little point lights to kind of give a little bit more illuminous into the scene, and it just makes it kind of feel a little more alive and a little richer. I've also got this cool day scene inside of here, and I'll just toggle that on. All I'm really doing for this is I'm literally just switching. I'm just switching between two different profiles here. So Let's turn the night one off. We don't want to have double lighting. And all that's doing is changing the post-process volume, the volumetric fog, and really the sun angle. That's really the difference between most of these two things is just some different fog settings and some slightly different, obviously the angle of the light's slightly different, and some slightly different tone mapping that I'm doing on the post-process volume. But they're really both very simple lighting environments, right? It's using sun-sky system, sky atmosphere, environmental fog to kind of give it that nice stacked look. And the end result is obviously a scene that looks awesome and it plays back extremely fast. I'm running on a really big piece of gear here. I've actually got a Blackwell Pro card in here, and right now we're projecting out in this room at 1080, right? So there's not a lot of pixels in that screen, and you can see a little bit of buzzing happening in those power lines. It's not too bad, and the reason it's not too bad is because I'm using a trick. In 5.6, we came up with a new thin geometry recognition for our temporal super resolution. So I'm using that foliage actor, that two-sided foliage on those power lines to kind of have that algorithm kick in and try to find that thin geometry. So it's a pretty good trick. Now, because I have such a powerful GPU in this machine, I'm actually going to go ahead and do something that's a little weird in a demo. I'm actually going to go and I'm going to overdrive my screen percentage because I just want it to look even better. So I'm going to put this up to 200%. And my performance is still going to be totally fine because, well, it's really, really fast in 5.6 now. So a couple of other things that are worth mentioning is fast geometry streaming. Hopefully I have my little sign working on here. Let's kind of zoom up here and see if this is going. Yeah, it is. OK, so check this out. So what this is this is just a little MP4 that's playing back in this window. This is city sample, and this is cooked onto a PS5, right? So same hardware, PS5 playing it. That's the original City Sample 5 with this fast-moving camera, really fast-moving camera going through that world partition. And you can see the world partitioning loading in on the lower left, on the lower side, and you can see how much faster that fast geo-streaming is with world partition in 5.6. So that's obviously got to be done in a cooked build, but it gives you an example of the types of performance improvements that we're trying to make with 5.6 specifically. For the PS5, which is well, actually not just for the PS5. This would work on any platform. But that fast geometry streaming is something that's super, super cool. So yeah, that's exciting. I think it's cool. Hopefully that makes sense to y'all. All right, so the next thing that we want to talk about are some usability improvements that we've been working on in the UI. So kind of quality of life things that you touch every day. That are going to have an impact. So the first thing is this toolbar is changed on the top. Obviously, it looks a little bit different than it did in the past. And what it does is it gives you, and I'm going to actually turn off tooltips really fast because I don't want to see those kick on all the time. So tooltips, if you turn tooltips to 0, it'll turn them off completely. And if you go ahead and use this summons delay, which is a really good tip, if you want them to still pop up every once in a while, but you don't want them to come up like instantly, put the summons delay to like 3 or 4, and it'll be 3 or 4 seconds. So I'm going to turn them off for this demo just because I don't really want to see them popping up the whole time. But that summons delay is actually a really useful way of kind of keeping them around, but not being so aggressively in your face. So this top toolbar, what we've got going on here is a couple things. Basically, you've got this little catch-all, right? So this catch-all has the ability to represent all the different functions for your translation, rotation, scale, snapping, displaying sockets and things like that. The most common ones are also pulled out here into the top bar where you can say, show me my grid snapping. Is it on or is it off? What percentage of grid snapping do I want? Same for rotation. So we brought the most common things out to the surface here. And we've made some slight changes over here. Like there's this use default scalability. So if I went to cinematic on this, right, you're going to see, OK, it still looks good. My performance is actually still, I'm probably going to run it like this actually for the rest of the demo because it does look really good. But you get this visual cue right now that's saying you're no longer on the epic defaults. And that's kind of what we're thinking is that kind of path to 60 where you're going to get 60 FPS for device profiles. If you're on epic, it should be like looking really good and get you to 60 FPS. So that's the goal. So that's why we have this like quick reset button if you've made a deviation. Now for this demo, we'll just leave it on cinematic because I think I have the bandwidth and the performance to do it. So why not? Another thing that's really interesting about this toolbar is I mentioned this is kind of a catch-all, right? Like it has all the stuff that's being redundantly displayed here. And the reason that it's cool to have this catch-all is if you had like a small window, so as I start to scale this, you'll notice the way things stack up in scale and actually all the windows in Unreal now it's just more intelligent in its ability to deal with kind of the redistribution of data inside of your display or inside of your viewport. So as I pull this, the outliner and the details panel over, you'll see that it starts to push into that, and those guys just kind of nicely disappear, but I still have access to those tools with that cascading dropdown. And the same thing will happen over here. You can still go back, and as the ones on the right start to disappear, there'll be like a little drop-down arrow that will let you get into them. Now you'll also notice that the content browser is acting slightly different. The way that the filters and things like that stack and tile also works in a much nicer way than it used to, as well as if you display objects, filtered icons, things like that, we've changed that behavior slightly too so that they also redistribute themselves and stack themselves up in a really nice way. Now, another thing that we've done is we've added in more levels for the actual icon display. So we have more granular size changes that happen. So you can use the control key and the middle mouse button to kind of scroll up and down through this. So you can see there's a lot more control there. And notice what happens when they get really small. The text disappears and you just have a color bar on the bottom that lets you know what type of things they are. So if you're looking at big 200 texture maps in a folder or something like that, you don't have to see all that extra little thing that's saying, hey, this is a texture map. Once you get down to the small icons, you don't need that information. So these are the types of things we've been working on in the UI to make it just a little bit more elegant and a little bit nicer to use. So I think with that done, we've kind of talked about performance, and we've definitely talked about, let's jump over to our slides. We've definitely talked about simplified user experience. So the next thing that we want to talk about is MetaHuman creation. So the MetaHuman workflow now lives directly inside of the editor. I think you guys probably saw that in State of Unreal. It's really awesome, and it's really, really fun. We've also improved the MetaHuman process, right? The metahumans look better. The fidelity is higher. We have 4 hero metahumans now, presets that are insanely high texture maps. The way we're synthesizing the textures is much better than it was previously, as well as some of the kind of base geometry and things like that are staying the same, but we're doing a better job of fitting. So if you're doing like a mesh to metahuman, something like that does like a fit of like a custom piece of geometry into a metahuman, the ability for that algorithm to do that shrink wrapping and fitting is a lot tighter than it used to be. So very, very big fidelity improvements to metahumans. And the tools are right in the editor, which is really pretty awesome. So let's just go ahead and I'll walk you through that really fastly. So I'm going to turn off that filter for the textures. So the process, I've already made a bunch of them. Like I've already got a whole stack of these little guys inside of here. And these are the 4 that are the most highest visual fidelity. So this lady, this guy, Bo, and then so there's two ladies and 2 gentlemen. And the process is literally you just right click and you say MetaHuman, create new MetaHuman. Now I'm not going to do that because I've already done it. I'm just going to pull up an editor of a character. Actually, we'll go ahead and do it. Why not? No reason not to do it. MetaHumans, create a MetaHuman character, and you know what? I'm not even going to name it because I don't feel like it. It's fun to just be crazy and not name stuff. Let's bring this guy up. So when you load up the MetaHuman Creator window, it's an editor inside of UE. Yay, awesome. We're not on the internet. Pretty standard. Look and feel if you've worked with MetaHuman before. So if we want to get to the material, if we just touch on this, as soon as we do that, it loads in a base texture of 1K and 2K. You can always download higher res textures. So the default display off the bat is kind of just built in. It's low res. If you want to get the higher res footage for each MetaHuman, you can go ahead and pull that down just like that. Now there are a bunch of presets inside of here, as I mentioned previously, and we'll just grab this guy because he's kind of fun to play with. We'll load him in. And directly inside of the window now, we can do all the things that we used to do with metahumans, like jump into the head, and you could start sculpting or deforming or transforming the points on the head, blending between multiple heads. So everybody here has tried MetaHuman, played with metahumans, experienced them? Yeah? No? Maybe? They're cool, and they're only getting better. And this guy only has the 1K texture, so I'm going to just kind of walk you through a few of the other things you can do with him. So let's zoom out and check him out. So he's been putting on, he's been eating, he's a healthy boy. So what we want to do is take him to the gym. We're going to go to the body. And inside of our body now, you could choose multiple presets and do that same MetaHuman blending thing with the little triangle where you can pick and choose influences. But we also have a new parametric model for the body. So really amazing. And you'll notice that the clothing on this character conforms and fits to him as I make changes to his body. So we have a new clothing type. You're going to be able to make your own clothing, throw them on Fab, sell them. The MetaHuman license has changed also, which is worth mentioning. So if you're using MetaHumans, it's just a standard UE license. So you can make a MetaHuman, take them into Maya, do something crazy with them over there if you want to. It doesn't really matter. We're going to basically make the terms a little bit more flexible for users. So if we drop down his weight a little bit, give him a little more muscularity, and you can see as I do this, the clothing kind of comes in there and it just starts to fit. It's just really, really fun to do all of this type of work with the MetaHumans. So after I've done that, the next step would be to go ahead and say, create a rig. So I've already done that, and I've already downloaded the high-res textures for this character, and it takes a little bit of time to process and do all that. Not a lot of time, but more time than we have in this demo, because I'm trying to plow through a lot of stuff. So let's go ahead and close that down and open up a guy that's already rigged. And we're gonna live dangerously here. We're gonna try to do some real-time MetaHuman capture, some facial capture. There's lots of different ways of animating MetaHumans and driving facial animation as well as body animation on them. Oh, hopefully this guy's going to come up. I double-clicked on him. Yeah, here he comes. It takes this thinking, processing. So I have an insanely fast GPU. Seems like my CPU might be like chugging a little bit there trying to open this dude. So we have multiple ways of animating characters, right? We've got the traditional AR kit, right, that used an iPhone. It uses a depth sensor. We've got the ability to use the iPhone with the depth sensor to record video and have MetaHuman Animator process it. That's going to be a really high quality film grade solve, as well as a multi-camera system, kind of the same workflow for that, so depth-based workflows. And in 5.6, we now have a new video-based workflow. And that video-based workflow would let you load a video background plate and have it in real time, very low latency for what it's doing, which is ridiculous, solve off of a video or a 2D plate. That same technology can also be used with this simple off-the-shelf web camera, which I have over here. So I've got this, and we're going to see if it's actually going to work. So I've got this camera, and what we're going to do is we're going to use Live Link to do this, and I need to go ahead and just go into Windows, Virtual Production, Live Link, and we don't care about ARKit. We'll blow that away, and we're going to add a source, and we're going to add a MetaHuman video source. And on that guy, we're going to grab this guy, this little camera, and we're going to say connect. And we'll put it up here. Now, this is literally the worst case scenario with the lights coming at me. I have glasses. Well, the glasses don't really matter, but the reflections on the glasses do matter. And those lights are blowing out that. So it needs to see my eyes. So hopefully it's going to pick up on my eyes with the bright lights tagging me. And I also have a hat on. So not ideal at all, right? Like literally not ideal. So let's go ahead and connect. And I might have already done that. I don't remember if I did. Oh, there we go. All right, cool. So, yeah. Yeah, it's pretty, dude, come on, that's cool. Yeah, hey, I got a clap. All right, I'll take the clap. So that was high risk, because I really wasn't sure if it was going to work. I'm glad it did. Okay, so let's let's close this dude down. He's gone, no more guy. And I also want to make sure I turn off Live Link, because we don't want that running in the background. Yeah, so I think that's everything we wanted to talk about with MetaHumans. Let me just double check and make sure that we covered everything off. As I said, there's a whole MetaHuman team downstairs in the expo. Go hang out with them. They'll show you all kinds of really cool stuff. This is a speed run. I'm going to go through stuff as fast as I can to try to cover off as much as I can. And I'm from New York, so I talk fast. So non-native English speakers, I apologize. The internet out there, I apologize to you all for how fast I'm going, but it's the way it's going to be. All right, animation. We are pushing hard to make Unreal Engine the place to go to animate characters. Whether you're doing real-time work, nonlinear offline animation, we want to make a world-class animation system. We've been talking about it for several years, and we keep chipping away at it, and it's getting crazy. It's just getting nuts. The things that we're doing, both from a refinement and usability perspective, as well as from a that's just insanely cool perspective, we're doing some really, really fun stuff. So let me jump into UE and show you some of the things that we've been working on. So I can just hit F10 and kind of get full screen here. Where is my guy? I don't think I have them on yet. You know what? I got to go over here and just do this. Let's go to bike. Where are you, guy? I forgot where I put the, oh, there he is. Okay. So I got a MetaHuman, another MetaHuman, right? He's got a bike. He's kind of doing this thing where he walks up to this bike and he gets onto it, right? Like pretty straightforward. Now, what we have now in 5.6 is a really nice workflow for doing editable motion trails. So if we go ahead and just grab this guy's, let's just hit G and get our rig up. Let's grab this foot. Okay, so I've got that foot highlighted. There's the keyframes on that guy, and we're just going to look at the sequencer curve so we can kind of see that. So with that foot highlighted, what I'm going to do is I'm going to go up here, and we now have this editable motion trail. So I've got some options set on this, so I've switched it from the default. I switched the style to dash, so that's going to be every other frame. It's going to kind of give me a zebra stripe going down it. It's more visually representational of what's happening with that. I've increased the size of it a little bit, and I've increased the size of the keyframes, and you can track things that aren't keyed. You can track any point on this character, and it'll make editable motion trails, and you can have multiple editable motion trails inside of there. So keep that in mind when you're working with it. And I think I have it set to show 10 frames before and 10 frames after. 17, a little bit more, but still pretty good. So I'm actually going to pen this guy, and with that penned now, you can see, ooh, let's just hit the F key and spin around that. You know, there's my editable motion trail in three-dimensional space. You can also have the motion trail be in camera space, which is really pretty awesome. So there you have two options for the way it's displayed. In this example, it's showing it in this 3D space. And obviously, as I scrub through my time slider, it's going to kind of wipe on and off. Actually, it looks like I don't have, let's set frames. We want that to wipe on and off. Yeah, so it kind of is now giving me this kind of before and after, so it's a little bit easier to see. And then, of course, you know, at any point, I can go in here and I can grab like a keyframe on this guy, make a change to it. It's going to update that curve, update the position of the foot, and allow me to manipulate this in three-dimensional space. So quite similar, actually, to the Maya's editable motion trail tool, which is good, because that one we did a really good job on back in the day, and this one's even better. Yeah, so that's some of the things that we've done to make working with animation data a little bit nicer. Now, you'll notice that inside of the sequencer, when I go to the curve tool here, I now have my tween tools directly in the UI. You can actually have that be a tear off and have a separate floating window for the tween tools too, so you can actually get two tween tools in there at the same time. So we've done a lot of work on that. I'll show you that in just a second. We've also added things like a lattice deformer for keyframes. We've done a lot of work on cleaning up the way curves are displayed and the way you interact with curves when you compress points down, how they stack on top of each other and delete each other and things like that. So lots of little things that are quality of life that you're going to feel right away when you start playing around with it. So we're going to talk about the tweening in just a second on another character here. Let's go ahead. Oh, by the way, look at all the lights that I have in here and all the graffiti, all my little decals. I went nuts placing graffiti everywhere. Like, I wish I had a can of spray paint. I would have spray painted stuff. I like graffiti. All right, anyway, we'll keep moving. So we've got these cool cars inspired by the 70s and 80s. And what I'm going to do is I'm going to switch over. Actually, no, we're going to do something else. We're going to talk about camera sequencer, and then we'll do that next step. So sequencer has had some really cool stuff done to it. It allows you now to you can use sequencer to do basically some really fun things where you can have multiple languages inside a sequencer. You can have multiple timings inside a sequencer, and we can use the motion warping stuff that we've been working on, so the blending and transitional warping, to go from gameplay into cinematic play. So go from a gameplay animation into a cinematic take, have that cinematic take happen, and then go back into gameplay. So that's what I'm going to show you guys now. We're going to jump into Pi, and yeah, hopefully it'll work. We'll see. I did hit play before you guys came in here. That's what we were waiting for. That's why we started 2 minutes late, because I was waiting for it to turn on and do all of its magic, and it should only take, like, hopefully a few seconds to start up. Yeah, okay, cool. And hopefully we have audio. Do we have audio on the computer? It does take a little second for the audio to kind of catch up. Okay, there we are. All right, so what I'm going to do is I've got another MetaHuman over there. Oh, and So as I said, this is based in City Sample, right? So inside of City Sample, we have a whole mass system for crowds, and the cool car system was done with mass, the traffic lights, all the blinking lights, all that stuff. So we just hijacked all that and shoved it onto these other kind of older looking cars. So it doesn't look like City Sample, but trust me, it really is City Sample, just with like a layer of coolness on top of it. So let's go ahead and run this character up into this spot. This is my transition, so I'm going to transition into this thing. And this is using a procedural camera. This is the new one, 5.6, highly experimental, highly experimental.
I don't have one. Well, my favorite is the giant octopus.
Dude likes giant octopuses. Man like me, I like giant octopuses. They're the best. So he kind of does that, and all that little drifting happening, if that MetaHuman was taller, that would update automatically because we use a procedural camera for that. So we saw two things in that. We saw, actually three things. We saw him run in there, hit a trigger, go from gameplay into a cinematic move. Then we saw the camera cuts happening with a procedural camera mover that kind of tracks his neck essentially. So if he's small or short, it's going to automatically compensate for that for your character. And we saw dialogue, and the dialogue is actually an important part because in Sequencer, we've added the ability to have languages. So if you've got different dialogue, often you're going to have different lengths. So you don't want to have to re-author everything completely from scratch. You want to use the same exact logic, the same exact clips inside a Sequencer. You just want it to be adaptive and work, and that's what we've done here. So let's just go ahead and escape out of this, and I'll show you that really. Ooh, got dark. What the heck happened? Oh, it's because I'm in the daytime scene, and then that plays in the nighttime scene here. Let's change that. Let's go to night. We're gonna get rid of the day. And we're gonna go to night. Yeah, he was in night, right? I think he was in night. I can't remember what I did. Anyway, my mind is like a marshmallow. Yeah, cool. So we've got this. Let's go into the details for that guy. Let's bring the sequencer up. And this is the magic, right? So look, here's our clips, here's our dialogue. That's how long it took, right? We're gonna switch to Japanese. Everything retimes automatically for that language. So now when we go back and play it, we're gonna get the exact same thing, but it's gonna take longer because it's longer in sequencer, and it takes longer to say the dialogue in Japanese than it does in English. So we're gonna do the same move, and we're gonna hear him discuss why giant octopuses are super rad in Japanese. If you guys notice, there is a giant octopus up there. This guy's actually like one of the better street artists in my environment, so he's spray painted that big giant octopus in the upper right-hand corner. I love the Manny. He's just like, okay. And again, that little procedural camera move that's just tracking his head. Yeah, so that's some of the improvements we've done to sequencer for gameplay, which is, and then it transitions back out, and I'm back to where I can run around and do my stuff. So pretty cool, and then look, here's this cool octopus. Yeah. All right, next thing that we're gonna do is get back to that tween tool and talk about control rig and some of the improvements we've made. Not improvements, like some of the added functionality that we've made to control rig. We've added the ability to have physics layer on top of control rig, right? So control rig physics is a thing in 5.6, again in the highly experimental category, but oh, so cool. This is like the coolest thing you're gonna see. Well, you saw Silver and the State of Unreal, so it's not the coolest thing you're gonna see today, but it's the coolest thing I'm gonna show you today. We'll leave it at that. Yeah, so we'll switch over to this guy. All right, bam. Giant octopuses are cool. As my dude was saying, giant octopuses. Yeah, they're funny. So let's go ahead and turn on our rig for this guy. So what we've got is we've got this guy, and if I grab one of these and start moving it around, it's a control rig, so that's like an end effector. And on that control rig, we have it set so that it stretches, right? So it's got the stretchiness. And down the length of each, there's like 18 bones down each tentacle. Each of those bones has a rigid capsule, essentially like a rigid, but it can scale, so it's not like truly like a rigid, but it's got a rigid body kind of embedded down the length of that. And that gives you the ability to do these really kind of crazy things, right? So as I move this around, you can actually tie it in knots, and you can do all kinds of really fun, interesting movements with this guy. Now, Actually, one of those legs is tied in a knot. So while that's happening, right, the other thing that you can do is you can go in and adjust on each one of these. We've got some controls, so I can basically say, you know what, let's unlock that leg. So that's just free. It's got a gravity, right? So I could zero out the gravity or make the gravity negative. It's going to rise up, or you have lots of control on that. And then there's this harmonics, and what the harmonics does is this is kind of basically just, you can see that little curve. That's a goal that those rigid bodies are kind of trying to get to. It's sort of like a little springy system that they're attached to, and it's just kind of recursively rotating down the lengths of those bones. So you start to get these really nutso movements, and it'll tie itself in knots. It'll wrap around itself, and this is all happening in real time, right? So it's like, as an animator, to try to animate tentacles moving like that would be super, super hard. This is pretty similar, actually, to what the setup that was done for Davy Jones back in the day. So the folks that were working on this and helped set this up had played a contributed part to that original Davy Jones rig. So this is pretty similar to that. And it's really, really cool. It's actually even more art directable. So I could go in here and I can grab like this one and say, you know what, I don't want it doing the harmonics, but we'll just unlock it so that it kind of flops around. And if I grab this character and I start moving him around, that's cool. I've actually got some keyframes on there, right? So we can transition between these poses. He's going to go up there and interact with the car. And this is where the tween tools come in. So I can use all these different tween tools to adjust that position. So if I do blended neighbor, it's going to try to blend more toward the front key or blend more toward the back key. So all these little nice tween tools work on multiple keyframes. Also, you can use it to inject keyframes in between things. And all of that happening on top of control rig with the physics. And I think this is so cool. I could spend all day looking at this guy. I don't know. I think he's really, really fun. And then there's some other stuff that you can do. Like you could turn off the control rig, or the physics rig, so it just goes back to being a standard control rig. You can turn that back on. You can disable or enable the dynamics. So lots and lots of control. And if I turn on visualize, you'll get a sense of all those little capsules going down the length of each of those tentacles, right? And yeah. So come by the booth if you want to look at this rig more in depth. I'm happy to walk you all through it and show you some of the other really fun, super cool things that you can do with it. So moving right along, I'm actually going to jump back into PowerPoint here, and we're going to talk a little bit about PCG and some of the things that we've been doing on PCG. So lots and lots have happened for the procedural workflow inside of Unreal. It's faster than it used to be. Architecturally, things have improved in the way the core system works underneath it. So it's not like a completely rewrite or anything like that. It's just lots and lots of improvements that add up to a much faster iteration process, as well as expanded functionality. The ability to spawn things on the GPU, for instance, is just a lot better now. So you can start to do things where you would have traditionally been using, sort of the old traditional open world workflows inside of UE, for foliage and things like that. In landscape, the landscape tools with the foliage tools and things like that. You can now actually do that cost effectively and in a small memory footprint and very performant by using GPU spawning with PCG. And we've got some really great biome tools inside of UE also that have also had some improvements. So we're going to jump in now, and I'll walk you through this. Again, very high-level overview of what's going on here. If you want to do a deeper dive, you can come talk to myself or some of the other people on the demo pods, and we'd be happy to kind of dive in a little bit more in depth and show you what's going on with that. So yeah, with this guy going, we can just actually close that down. We don't need to do that. And I think I've got my stuff set up over here. I do, yeah. Oh, so this is pretty fun. I also went through, and the original city sample had like sticks for trees, because that's what we could do in the time we had, and also like performantly. But this is actually the trees that are taken from the Electric Dreams demo that we did. So I think that was probably 5.3 was Electric Dreams. So I went through and found all the blueprints and replaced all the actors in the city sample like stick trees with these Electric Dream trees, which are awesome. So I'm taking two sample projects and smashing them together with all that stuff I grabbed from Fab. And again, that thin line rendering support, that two-sided foliage thin line rendering support in 5.6 just makes the foliage look better. It does a much better job of kind of dealing with that aliasing issues and things like that. So it's a lot of talking about trees, and I'm not really demoing trees, but what I am demoing is PCG and how we can use it to make shipping containers, because why wouldn't you want to make shipping containers procedurally? I don't know. It seems like a good idea to me at the time. So a couple things. First thing is just from a workflow perspective, like if we go back to our content browser, and I just kind of come down here. Again, city sample, right? Tons and tons of folders. If I right-click and I say create a PCG graph, we now get a pop-up. So kind of similar to like Niagara, right? So we have preset templates that you can start from. They're great learning tools, right? Like you can jump in there and rip them apart and see how they're done. Now, one of these is this PCG create geometry, create mesh, right? I took that and I made my own derivative of it. So mine is based off of that, but I added in the functionality like I modified it to work with to make shipping containers. But it's based off of that create geometry one. So I'm going to just start from this. So we'll just say initialize from template. We'll call it PCG graph demo. Hopefully this will work. I spelled it wrong. That's OK. No one cares. If we double click on this guy and bring it up, here's the graph window. And I'm actually going to go ahead and just drag this into our environment also. Boop, boop. All right, cool. Look, it made a procedural shipping container for me, right? Just like that. Notice that as I move it around, it updates the doors. They're dynamically kind of just getting random rotation. So every time I dirty this, it's going to give me a different rotation on those doors. So I'm going to walk you through the graph and talk to you about what's going on here, all right? So here's our graph. There's been lots of improvements to the graph editor. The first thing that you're going to notice is there's a viewport in here, right? So you can visualize what you're working on for certain things in the viewport. So we're doing two things in this graph. We're doing some procedural generation with dynamic meshes, right? Like what I wanted to do is I wanted to be able to make those shipping containers be different lengths, right? And I didn't want to just like try to stack up different numbers of like vertical beams or something like that because I liked the way the texturing worked. I wanted to just use a Boolean operation to chop off the end of it and then cap it with another piece of geometry. And that's what we kind of have right here. Let me just pull this back down. I've got the original container over there. I've got this back end that I just kind of use the modeling tools to smash together, and then we've got the door. And what I'm not displaying is I also have a polygon cube in there that I'm using as a cutter. Literally, it's just a polygon cube that I called cutter that's going to do a Boolean operation. And so what we can do is if we look in here, this stuff right here, this was the original. The first thing we're doing is we're looking at the editor and we're saying, all right, cool, let's create some dynamic meshes from it, right? So we're going to do the static mesh from element, and I don't remember which one this is, but let's just double click on this. Yeah, so that's the original piece of geometry, right? So I'm getting that, I'm turning it into a dynamic mesh. I can visualize it in my viewport. Yay, awesome, cool. The next thing that I'm doing is I'm getting this guy, which is my cutter. Then I have my little door, right? So those are my three pieces of geometry that I want to work with. Now I'm doing just a transform, and on that transform, I've got this thing called cutter. So that's just giving me an offset, and this is actually a parameter. So we've got a window now that pulls all that the graph parameters out into a separate window. So it's a little thing. You could do this before, but it was buried in the details panel. It was hard to get to. So now with the graph parameters, you get all of that exposed at the surface level for you. You can rearrange it. You can drag and drop them into the graph to start using them and like doing like a get from it or something like that. So the workflow has changed substantially inside of this. We're not doing anything new here per se. We're just cleaning up the workflow and having the ability to visualize it. So then we go in here and we do this transform. We're kind of moving it in space. I do the Boolean operation. So I cut off the back, and then that guy is transformed to the same spot. That one transform node moves the cutter as well as the back wall. Their pivots are in the same spot. So then we just kind of merge that stuff back together. This is a dynamic mesh still, right? And then on top of that dynamic mesh, like I want to spawn the doors. And the doors don't need to be dynamic, so I'm just using standard static meshes for those, right? The idea is you use dynamic meshes where you need them. You use static meshes where it's going to be more performant. It makes more sense to use a static mesh for the doors because they never change. Now, after you've made these dynamic meshes, you got to make a choice. What do you want to do with it? Do you want to spawn it at runtime? Do you want to save it off into be an asset in your content browser? And that's what we want to do. Is we want to save this out. Like once I've set the size of this guy, I want to save it, right? So you'll notice that the save asset is like right here, right? So I turn on save asset. It's going to bring up my thing, and I'll just say save. It might be unhappy because I'm not on Perforce. Yes, that's fine. So I've saved that out. cool, now it's no longer dynamic. Because once we do that, there's a little bit of logic that says, oh, okay, cool, you've saved, forget the dynamic part of the graph now. Now it's just literally an asset that we're bringing back in, right? So we bring that asset back in, and we use that to find its sockets. So that basically on the original static mesh, I have sockets, and the sockets are going to let me position my doors, right, as well as the graffiti on there. So we're going to use that to then do this sort of standard PCG workflow on the top. Now, the way it's set right now is it's saved at the disk, but every time I make a change to that blueprint, like if I drag that blueprint, it's going to resave it. Every time it's dirty, it's going to resave it, right? So to get around that, because it's a demo, what I'm going to do is I'm just going to basically tell it to stop saving it by unenabling that. So now what I've got is, my mesh comes in, I've got this static mesh over here, there it is with its cut thing, and then inside of here, at any point, if I wanted to, I could start to do some changes to this. So we're grabbing our door sockets. I'm doing I'm basically finding point 1 and point 2 and deeming those doors, and from that spawning the doors, and then point 3 is my socket. Index 3 is the socket for the graffiti, so I spawn off the graffiti. Now, what I want to do is for these static spawner of this mesh, and I want to make sure it's a static spawner for the mesh. What I'm going to do is I'm going to go ahead. Yeah, that's the right one. I want to change the random on this. So I think I have it set to be. I got a max value set, but I don't have a min value set. So what I'm going to do is I'm going to go ahead and on this min value, rotation min, I'm going to create a new constant. So I hold down the 3, click the left mouse button. It creates a constant. And I'm going to right-click that guy, and I'm going to say convert to graph parameter. So as soon as I do that, it's called new property, conveniently. Like, OK, great, whatever. But there it is, right? So I've just made a new graph parameter, and I can use that to pipe into my rotate min. And then I can go in there, and I forgot what axis this was on. Let me look at this guy and see. Yeah, it's 33. So if we take this guy and we do something like 88, now it's going to randomly rotate those doors between those values based on that new property. And I think if it all works, I can duplicate this guy, move it out, and you can see, oh, the graffiti moved, the doors have a slightly different rotation. This one's open a little bit more than that one. And that's kind of cool. Now, also, the debugger has the ability to see stuff directly inside of here. Like it didn't used to give you as much information as far as the tree of the graphs over here as it does now. And you can actually go in here and have it use this to take you to the actual object of which one you want to pick. So tons and tons of little workflow refinements just in the PCG graph creation window, right? Like that's really cool and super, super fun. So we're quickly running out of time. I've got 7 minutes, and like I said, we won't have time for Q&A. I'm sorry. But I will talk to everyone downstairs at the demo pods, and there's a bar next to me too, so it's like the best spot. So come hang out. It'll be super fun. All right, so the next thing I want to talk about is biomes. So we have a biome tool. It's version 2, biome tool for 5.6. We call it Biome Core 2.0. It leverages all the improvements that have been made to the way the PCG system works. So the performance improvements it leverages. It stacks on top of that. And it has its own host of improvements to both performance and workflow. And I'm going to give you a quick overview of it really, really fast. Hopefully we have time to create a coastline after I give you a quick overview. And the way I'm going to give you the overview is actually with the sample content, because the sample that it ships with, it's an actual plugin. So you have to load in the Biome Core plugin as well as the Biocorm sample plugin. And that sample plugin will give you a scene and all the little stuff to kind of really see what's going on and understand what's happening with it. So I'm going to open that up. We're going to open up this sample level, and we don't need to save anything. And I'll give you a quick overview of what's going on with this guy. All right, so here's our world, and it's using the Biome Core. And you can see as I get close to this, that stuff starts to come in. All those little objects that are zooming in, these little spheres, the little things on the ground, those are all being spawned on the GPU, right? Like that's being generated on the GPU. So they're super, super fast, very performant. and fit into a small memory footprint, right? So that's a great, great thing, this GPU-based spawning. That's all built in using sort of an assembly workflow, right? Like you teach the tree how it's supposed to spawn its things. The biome tool has been reworked. So the biome basically has the biome core, which is the big box that floats around it. And then inside of those biomes, we've got all these other little biomes, right? These little squares are basically different types of biomes. And you can generate these biomes. If I bring up the outliner, this will make more sense. So you can have spline-based biomes. You can have texture-based biomes now, much easier than you could before. So you can use like, RGB values to paint 3 different colored masks or an alpha or any color you want. So you can do some texture-based stuff. And the thing that's really interesting about the biomes is the way that they're handling it is much more performant because the biomes themselves have the ability to take care of all the creation of the points themselves. So that happens locally. These are local biomes. They handle the creation of the points themselves, and then they basically report back up to the core biome, and that's where the spawning actually happens. And it's really smart about it, so it doesn't like spawn double things and then try to cull them. All that stuff happens in the core. So the little local biomes report up to the massive core biome. The massive core biome handles the actual distribution of the actual creation of the points and the geometry and the things like that. Now, on these local biomes, you can have kind of recursive children relationships set up, and you also have blending relationships, like which biome has a higher weighting. Does the biome have a hard cut or is there a feathered edge? When it gets to the its neighboring biome, how do you handle the transitional areas between those? And they're all handling the things like when a biome spawns a tree, or when the rocks are spawned, the trees know not to spawn from where the rocks are. And all that stuff is kind of illustrated in this sample content. So get it, dig around in it, and check it out. And I think it'll make sense to you all when you play around with it. And it's just really, really fun. And there's several different types here. You've got this desert. I think there's, where is it? Somewhere in here is that. This one's cool. So this one's using, this is like a little farm one. Really, really fun. And where all this stuff lives, everything that's being made with that actually lives in the core biome. So in the blueprint section, this is really where you really want to get. Is in the blueprints, you're going to have everything to create all of these base types of biomes. You drag the core biome in, then you start dropping your other stuff in. And I'm going to show you that right now. We're going to build some cliffs back in that other scene. But that's a quick overview of how it works. And I've got 2 minutes to do this. I can do it in 2 minutes if my scene opens. And it's a big scene. It does take some time to open. I'm not going to lie. And I'm not going to hit play because the first time you hit play, it takes some time. It's 10 seconds after the first time, but the first time takes a bit. All right, you can do it. It's a nice silence that we can have between us because we're all good friends. Doesn't matter. It's all good. All right, let's go in here and get rid of my secondary. We'll just use the day model. Where are we going to go? We're going to go over here. We're going to hit 5. All right. It's the day, but it's not that good. Good grief. Let's get some sun on this. All right, what I want to do is I want to generate some cliffs, right? So to do that, like I said, you go into core biome. So in core biome, you go into blueprints. In the blueprints, the first thing you want to get is your biome core. So BP biome core. You drop it in. Then on top of that, I want to get a volume that I want to spawn stuff out of. So we're going to get a biome based on volume. We're going to drop that in. So this is a local biome, localized region where we're going to spawn stuff. And what we want to spawn on this guy, so if we go into our details, I'm going to just hit F10 and bring all that stuff back. No more world partition. We don't care about you. All right, so in this guy, we've got our biome. We're going to add a definition. This would let you visualize where those go. The definition process, you make these, you define them. They give you a color. It lets you, it's a kind of it's a workflow thing that helps you really see what's going on. I'm just going to, you don't have to have that, by the way. It would work without it, but I'm just turning it on. So we have 2 choices. We could load in an asset. So an asset would be like a pre-configured thing that you might use over and over in multiple local biomes. Or in this example, just to make it go a little bit faster, because I've got 40 seconds, I'm going to just use a local biome. And in this local biome, I'm going to add a local asset. That local asset is going to be index 0. We're going to give it a generator. So the generator, we're going to start with just shared rocks for now. That's going to randomly distribute stuff. These generators come with it. They're PCG graphs. They have some logic in them. They're already out of the box, pre-wired up for you in the sample content. And we're going to give it a mesh, and we're going to call this mesh cliff 3. All right, and just like that, okay, we're randomly distributing some Irish coast cliffs around there. Now what I want to do is I want to use a different generator. I want to use a generator that is set up to find ISO lines. So we have a line of where is it? Not shared rocks. I'm going to use my version of this. So there you go. And what that's doing now is it's finding the cliffs, essentially. So if we double click on this and we play with some of these parameters, we'll bring up this instance. Doink. All right, so what I'm going to do is right now it's basically got, here, if we display our points, you can see those are the lines, right? So what I want to do is you can tell it to be the top, the toe, the crest, or the toe. We're going to do the inversion of those two, and we're going to turn this off, and we'll just give it more spacing. So we're going to cull some stuff out by making the spacing a little bit bigger. And I've got 50 seconds to do this. Something kind of like that. And just to speed it up, I'm actually going to make this be a little bit smaller and drop it down ever so slightly. Oh, what did I do? No, come back. I'm over time. Oh my gosh. All right, I'm over time. It says 0. That doesn't feel over to me. It's not like negative flashing. Oh my gosh. All right, well, come hang out with me. I'll show you how to hook up the runtime thing downstairs. Thanks for your time, everybody. I'm sorry we went over. I appreciate it. I'm over by 2 minutes. I could have finished that in 30 seconds. It would have been 2 minutes and 30 seconds that I was over, and you would have saw grass on top of the cliffs. But whatever, it's fine. Thanks again, everyone. Enjoy your Unreal Fest. Thanks for joining us. We really appreciate it.
started. Please silence your cell phones. This session is being recorded and live streamed. Hi, Mom. And I will have a QR code for y'all to scan at the end of the show. It's going to have some links and a bunch of resources related to the thing we're talking about today. So put your phones away. Don't take pictures of the slides. And I'm not going to have a whole lot of time for Q&A in the hallway after this one, but I will be at the Dev Hub from like 1:30 to 3 o'clock tomorrow. So if you want to come chat more, you can find me there. And last note before we get started, you'll be getting surveys from us through the CVN app. Please fill them out. It helps us make the show better and better for you every year. So that out of the way, let's get started with the show. Howdy, y'all. My name is Matt Ostale. I am a senior technical artist on the developer relations team here at Epic Games. And today I have for you a literal fever dream that I had about using Niagara to represent and interact with the units of a real-time strategy game, and I decided to do it on a phone as a little added challenge. So let's take a look at what I've got. So what I've got here are about 4,000 units, and you can see they're all little flipbook sprites, but I've got like the little health of the units. I've got all these different units here, and I can come over here. I can select these units. I can tell them where to move. And these are all, it's just one Niagara particle system, right? You can even see that the units are kind of getting out of each other's way and trying to go where they're supposed to go. And of course, we've got a little fog of war effect going on in the corner, right? So pretty cool, a lot of fun. And I wanted to talk about this in the context of a real-time strategy game because there are a lot of challenges in a real-time strategy game that are difficult to overcome using some of the built-in sort of normal pathways you might take in the Unreal Engine. We've got a bunch of things that are all relevant to each other, all relevant to gameplay, need to be interacted with, need to be kept track of. And the thing is, you shouldn't use just characters to do this, right? The A character base class with a skeletal mesh and a bunch of bones and a collision capsule and navigation, it's not necessarily the right choice for this specific application. So we need a system that can efficiently represent the units, allow interaction with the units, and the units to interact with each other, store information about those units, and share information about those units with other systems in the engine so we can do some cool stuff with them, right? Now, there is a system for this in the Unreal Engine. Does anybody know what it's called? Raise your hand. Yeah, you in the back. What's it called? Data channel? Wrong. It's called Mass. Mass Entity is a framework for data-oriented calculations using entities, fragments, and archetypes. Mass Gameplay is a plugin that builds on that includes functionality for world representation, spawning, lotting, replication, even state tree. There's also Mass Avoidance, which uses forces to get all of your entities to avoid each other. It's really, really cool. And the thing is, Mass is objectively, in my opinion, the right system to use to build a real-time strategy game. But I am a tech artist, and that sign can't stop me because I can't read. So strap in. Because really, to me, this talk is about bringing the fire of graphics programming to the tech artist. And if I suffer avian consequences for it, then so be it. So what are we actually going to learn today? Like I said, there are interesting challenges with the real-time strategy genre. It gives me a really easy framing to introduce to you some really powerful tools and techniques with much broader applications in a cohesive way. So we're going to learn how we can use Niagara as a compute shader to represent and drive the logic of our units both on the CPU and the GPU. And while we're in Niagara land, we'll get a quick example of how to use neighbor grid 3D so our units can avoid each other. And we're also going to learn how we can pack a lot of information into a single float. And finally, we'll use the information from the Niagara system to draw a distance field for the fog of war effect. Ready to roll? Cool. All right, so let's talk about compute shaders. You've probably heard something, I've probably even said this to you, that Niagara is basically a compute shader. And compute shaders are basically a shading stage used for computing arbitrary information, not meant necessarily for drawing pixels or triangles. And all it really is we're taking inputs from the CPU, handing it off to the GPU, said, hey, can you run some math on this? And then we can get the results back onto the CPU, right? Optionally. So we're going to start in Niagara, of course. I've already done a little bit of setup because I know this demo is going to be a little tight for time. But basically what I've got here is a GPU sim particle with fixed bounds already set. I've got a bunch of user parameters. So what we're going to do in our little demo today is not the full thing that you saw. Again, tight for time. But we're going to take our little particles, we're going to give them random goal positions that they're supposed to move to based on relative to where they are. So instead of just constantly bouncing around the screen, it's to say, okay, you only move 500 units away from where you are. So we've got an input vector array of goal positions that is set to sync CPU to GPU. We've also got another user parameter here called out positions, and this is sync GPU to CPU. So we're going to write the position of the particle into this array from the emitter and then read that back in Blueprint. And just as a little pro tip, definitely set the max elements on that, otherwise this won't work. So that's all of our setup, and then I hit Windows D because I'm really good at my job. There we go. There we go. And then I've also got a texture render target user parameter down here that is set to RGBA32F because we want to have 32 bits of precision for this. And then, so I've set that emitter property over here so everything links up nicely. I've also got a module here that basically initializes the size of the render target and the size of the output array to match the size of the input array. So this is going to be our kind of source of truth. And then down here, I'm spawning particles in a grid because I didn't want them to collide with each other right off the hop. And I think that's all I've got. And we can start getting into it. So the first thing we're going to do in our particle update, we're going to create a new Scratchpad module, which we will name Move Units Toward Goal. And we need a few inputs to this. One of them is our vector array. And another is the unique ID. The thing I forgot to mention is that this particle this emitter is set to requires persistent IDs because the thing that matters, the thing that identifies this particle between both systems is the index in the array. So the 0th particle is the 0 index in the array, is the 0 position in the render target. We can associate all those things together. So we use unique ID, not execution index. And then finally, we need the current particle position because we're gonna push it toward that location. So I'm gonna grab the vector array and I'm gonna say get a value off this vector array. And then I'm gonna grab the position value. I'm gonna say truncate, please. And then I'm gonna convert that to a vector so we can just operate in that space. And then in order to get the direction from the current position to the goal, we just do a little subtraction. And then finally, I'm gonna multiply this by a optional scalar value, which I just conveniently convert to a float and drag that on as an input, which we're just gonna leave named as is. And then we're going to set a vector value on the output here, which we're going to call physics force, which is in the transient namespace. And so this is gonna say, hey, this is how much force is currently applied to this particle. And then what's really nice about this is that that's then going to get picked up by this solve forces and velocities node, right? I'm just telling the forces and velocities solver, here's how much force we have to work with, okay? And then I always have to make sure that I link my inputs. So we're going to start with the goal positions. And then I'm going to set the magnitude to 1. And you can see the particles are going to start moving. So they kind of swapped positions because they didn't get spawned in their right spot. Then I can go over into the goal positions array because I've got this set up as debug, and I can say, hey, you're actually supposed to move much farther away from each other. So a little bit of debug there, but you can see, everything's working. I've got these little sprites moving around. And then next up, we're going to jump into the blueprint. Oh, next up, we're going to finalize the particles because the blueprint needs to know where these particles are. And to do that, I'm going to set up another simulation stage. And all this really is like, hey, I've got a thing in the emitter and I need to iterate over a bunch of things. And the default iteration source is particles, but you could also do something like a grid 2D or even a grid 3D, links at the end of the show. And in this one, so it's like, all right, now that we've done all of our particle updates, now we're gonna reiterate over all the particles now that we know where they actually are. So I can create another Scratchpad module, which is we're gonna call finalize units. And same thing, we need a vector array input, but this is going to be the output array that we're going to be writing to. And we also need the render target data interface that we're going to work with. And then, of course, the unique ID. So then I can just set the array element over here to the particle position. There we go. And I'm going to convert that to a vector just the way it is. Totally fine. Actually, I want to truncate that because I bet I'm going to get a warning if I don't do this right. convert numeric to vector. There we go. And then we make sure that we set that unique ID over there, plug everything in, and then we're going to, because we're going to set a value on the render target, so set render target value. And then you notice I've got X and Y index, and we all know that there's a certain amount of math that we could do to get this correct, but luckily, we can just do a linear to index so that I don't have to remember all that math on the fly, because there's a lot to cover. And then finally, we're just going to set the value in the render target. So now we've got a render target that knows where the particle is, and we've got the CPU is going to know where the particle is. We're going to do stuff with the render target later. It'll be really cool, trust me. All right, so that's the setup on the Niagara side. Now we're going to jump over to the blueprint. I've already got some of this stuff staged already. So you can see I've got a certain number of particles. I resize the array accordingly because this is the thing that's going to tell the particle system how many particles to spawn. And then I'll grab my Niagara system component, and I'll say set array, set vector array. There we go, and plug everything in. And then when I was setting all of this up on the blueprint side of things, I called everything goal locations. And on the Niagara side, I called it goal positions. And for that, I will burn, and I apologize. And then we're going to set active on the emitter because all of that initialization is happening on spawn, so I set it to not auto-activate until we actually get the values in the right spot. And then I've got this set timer by event over here, and so every 3 seconds we're going to trigger this function, which is going to get the values from the Niagara system. So we're going to get vector array, and that will be our out positions. And then we're going to iterate over this array, because again, the 0 array in the goal position, the zero position in the out position, so those are the same particle. So then I can know where that particle currently is, and then I can set a new goal location for it relative to its current position. So we can drop that in there, and then I had to remind myself, because every time I did this demo, I forgot this part, and I wondered why it didn't work. So then we have to do the set array vector again to wrap everything up, so that'll be the goal positions, and we can update everything accordingly. Yep. Okay, so fingers crossed. Yeah, all right, so I've got 64 particles. They're moving toward the center, and now you can see they're starting to spread out. They're going to go start randomizing their locations, and because I didn't think that was far enough away from everything, I'm going to set that max distance away to something like 500. There we go. So I jump back in, play in editor. So 3 seconds, and then we're going to start scattering around. So because I know where the particles currently are, I can tell them to go somewhere else. And they all went out in a circle because that was, they all started from 0, 0, 0. But maybe I actually want these particles to kind of bump into each other. And we'll get to that in a second. So again, this is basically what's happening with my RTS here, is I've got all these units, and I know their locations in the world. I can project that to screen space, and I know this my little marquee selection box. So anything inside that box, I say, hey, you're selected, and then when I double click, if you're selected, I update your goal location and send that back onto Niagara. Super easy. So that's basically it, right? We tell the GPU to do some work for us on data that we've provided from the CPU, and then we can get Niagara to give us the results back. Pretty straightforward to me. But I want those units to I want my sprites to kind of bump into each other. I don't want it to just be, going straight to where they're supposed to go. And the thing that you don't want to do is this. For each particle, go over every other particle, calculate the distance to it to figure out what its relevance is, and check the distances between, because then that's another square root operator, which is super expensive. And the reason that this doesn't really work is that the complexity of this calculation will increase with the number of particles. So 10 particles, totally fine. 100 particles, you're already in deep trouble. Luckily, we have something for that. It's called Neighbor Grid 3D. And it's basically a giant grid with different grid cells based on your parameters. And it's storing the index of the particle in that grid unit to say, okay, if I'm in 0, 0, 0, I've got particles 2, 10, and 12. And that makes it really easy to access, and we can do other stuff with this. And it also means we can bound our calculation to the 27 grid cells around us So the 9 on the bottom, the 9 in the middle, the 9 above, and it caps the number of neighbors that we're going to have to iterate over so that we can, again, keep the complexity of this calculation a little lower. So we're going to jump back into Niagara here, and we're going to get this set up. So I didn't want to stage all of this stuff to begin with, so bear with me while I create our emitter properties. So the two things that we're going to need here are a neighbor grid 3D, and we're going to need a attribute reader, a particle attribute reader. And this is sort of the data interface we will use so that when we're working on one particle, we can figure out where the other particle is. And then to get that set up, easy to set up the attribute reader, we just drag it over and say, hey, this is the emitter that we're working on. We are working on ourselves. And then we need to initialize the neighbor grid 3D, which luckily comes in a handy dandy module, but it is not in the library, so you got to turn off library only. So initialize grid 3D. And then I'm going to set that to, like 5,000 units, 5,000 units. Pro tip, if you set the local pivot to 0, 0, 0, and your particles are starting in the bottom corner, things will get a little weird. Don't ask me how I know. And then I'm going to, just for the sake of argument, I'm going to set the max neighbors per cell to 15, and then I'll set my the number of cells in any given direction to 15 as well. But you would want to customize these to suit your needs. And these numbers don't actually work because I'm doing everything on the XY plane. But for the sake of argument, we're going to do it that way. All right, so next, initialize grid. Oh, and then I have to set the emitter property that I set up earlier, this neighbor grid 3D, to the output of initialize neighbor grid. Otherwise, things will go a little skew-if. There we go. Okay, so I've got the particles, and I know where they are after I've done the initial solve forces and velocities. Great. Now I need to iterate over all of those particles again to store their indices in the neighbor grid 3D. So I'm going to do that with another. I'm going to do that with another simulation stage, which we're going to call populate for the sake of time. And then we'll add a new module, which is the populate neighbor grid module. Easy peasy. This takes a couple of inputs. It's just our neighbor grid 3D. There we go. It's already set up to grab the particle position. And then we need the world grid, world, come on. Oh, there we go. World to grid unit matrix. And this is going to help everything transform into the right space. So that's going to put up to the max number of particles we've decided into the neighbor grid 3D. And then we're going to get another simulation stage going, and this is where we're going to do our avoidance. So that's another grid, another value, and we're going to need two modules in here. And first we need solve forces and velocities again, because we're going to push the units away from each other. And then we need a scratch pad module, which we will call avoidance. And this is going to look a little scary, but it's OK. We're going to walk everybody through it. Ready? It's fine. It's fine. It's actually, this is a stripped down version of something that we've got in our content examples, so definitely check that out. But what I've got here is sort of the core logic of our avoidance. And while I set up the inputs on this module, if you'll bear with me for just a second. So I need the unique index. Plug that into the instance index, random unit vector. While I was working on this demo, I realized that there was this weird issue where the particles, if they were directly on top of each other, would explode away from each other. So if they're really close together, I just kind of offset that position as a little wink and a nudge. There we go, we plug that bad boy in. And then our output value here, again, it's a force, so we're going to say, hey, the output here is this transient physics force value. Change namespace to transient. There we go. All right, I'm going to walk you through this, and I'm going to zoom in real good. So up at the top here, all we're doing is initializing our output parameters. So our repulsive force, how much we're going to push everybody away. And then I've got this array of instance index offsets. So if the bottom left corner of the 27 grids that we're going to work with, that's -1, -1, -1, and the top right is +1, +1, +1. I'm just storing all these in a flat array to make things a little easier on myself. Don't have to do a bunch of nested for loops. And then this is really important. You have to, when we're compiling this HLSL, we have to make sure that we're only compiling this section if we're doing a GPU simulation. Otherwise, things fall apart. And then this section here, or these first two lines here, we're going to figure out the position of the particle in 0 to 1 space relative to the neighbor grid. And then we're also going to get the index, the grid index of our current particle based on its 0 to 1 position. So that's all this is doing. And then we get the num cells, the max neighbors per cell, and we start iterating over all of those index offsets. And then we're iterating over the max neighbors per cell. So the most number of iterations we can ever do for any of these particles is 27 times 15, which is a lot simpler if we're dealing with 4,096 units, right? I'm only working on that little bit of math. And then the next step that we're going to use is figure out what the grid cell offset we're working with. If it's -1, -1, if we're in 2, 1, 1, -1, -1, -1, now we're in 1, 0, 0. And we figure out and using that value, we can grab the current neighbor index. So that's, I've only got 15, 0, 1, 2, 3, 4, 5, 6, 7, 8, 10. I'm going to store that in this neighbor linear index value, and then I can do this get particle neighbor to get the particle index of that particle. And now I have stuff to work with because I can use the attribute reader to get the position of that particle. And then all we're doing down here is checking the distance between the particles. If it's within our sort of overlap range, we're going to start working with it. We get a normalized vector away from the other particle. We push it away, increment the neighbor count value over here, and then all we do is just average the repulsive force by the number of neighbors. So if you've got 10 neighbors, we've accumulated this sort of direction away from everybody. We're going to average that together and then multiply it by the repulsive force strength, and we'll get to this last line in the next step. Cool. So I will set up all of put that in the right spot, and then I will set up I dragged this position value over here, and I needed to make sure it's the particle position. Easy. Almost messed up. So then we're going to grab the neighbor grid 3D from our emitter, and then we're going to get our attribute reader. Here we go. And then our world 2 grid unit. So that's going to get everything together. And you can see these particles are already kind of fighting to be where they want to go. And I'm going to make that even worse for them by making them all go toward the center. So because I set the repulsive force really, really high so that you could see it, they're all trying to get to 0, 0, 0, and they keep bumping into each other because I set their overlaps really, really high, right? So that's all we really needed there. Here's what that looks like with 64 particles. And you can see things get a little hectic, right? So I'm doing an interesting calculation in Niagara, and I can do some really cool stuff with it. And again, that's basically the same thing that's going on in our giant example. They're all trying to go to their goal positions, and they're all kind of pushing each other out of the way. But I lowered the overlap value in the forces here because I thought these guys might be a little nicer to each other. But you can see, like, as I move these units away, these guys are like, oh, okay, well, I'll give you space. I'll give you a little space, right? Cool. So we really quickly learned how to use Neighbor Grid 3D, how we can use the built-in modules, right? Initialize Neighbor Grid 3D, populate Neighbor Grid 3D, and how we can access positions of other particles from within, from a current particle evaluation. We can make those repel each other. So now, as I take a sip of water, now let's talk about how we can efficiently store state information, any kind of arbitrary information about our particles, our units, whatever thing we are operating on in Niagara, into a single float. Because here's the thing. Colors are just proportions of red, green, and blue light, right? And those proportions are represented by numbers, 83% red, 23% green, 100% blue. Now here's the thing about floating point, 32-bit floating point numbers, is 32-bit floating point numbers are actually 32 booleans wearing a trench coat. Thank you for sticking with me on that one. So why go through all this effort, right? It's a memory efficiency thing, right? I've got one number, so let's say, we want to, in our material, know about the number of neighbors that we've got around us, right? How many people are overlapping? How many particles are overlapping us? Maybe I want to know the current index grid cell that it's in for whatever reason, and maybe it's a distance to its goal position, right? And we could use dynamic material parameters for that in Niagara and just pass that through as about 5 different 32-bit floats, which ends up being like 160 bits. And if we multiply that out by our 4,000 units, that's like 600,000 bits, y'all, which is almost 600 bytes. Okay, I know that that's not like huge given the machine that I've got under this desk, but maybe it's not about memory efficiency, it's about efficient use of the channels of data that's available to us. You only have 4 UV channels with Nanite. You only have 32 custom primitive data floats and per instance custom data floats, maybe and 16 dynamic material parameters. Maybe you need to be efficient about the channels that you have available to you. So I need to pack more information into a UV or a dynamic material parameter to make room for the other stuff, because I don't actually need all of the precision of a full 32-bit float to store the index, to store the number of max neighbors, because the maximum number of neighbors is only 15. So let's jump into a material, and I'm going to show you a really handy node to help you conceptualize how all of this stuff works. So I set this up real quick. I've just got a custom expression returning a float into the debug binary values float. So we're all probably familiar, I hope, with debug scalar values, right? So this is just going to show me what that float number is. These are very handy for debugging stuff in materials all the time. And then if you have an interest in doing what I'm about to show you, this debug binary values float is really, really handy. So we're going to zoom in on that so we can see that. And then we're going to zoom in over here so we can see that. All right. So instead of returning 1.0, maybe I have an unsigned integer called value equals 0. And then I want to, because we're going to use a float anyways, so we're going to kind of think about float space. So what I can do is instead of returning the value converted to a float with just like a float like this, I want the bits of the value to be treated as a float, which is a slightly different thing. So we're just going to return that as float, super handy. So we'll return value as float. And of course, a value of 0 is 0, but maybe I can use, I don't know, 16 of these bits. So 16 bits gives me about 65,535 steps of information, which is more than enough for me to store a rough approximation of a current particle's position to its goal position, right? And that is very handily represented by the hexadecimal value OXXF, right? So that is my first 16 bits, or if you wanted to, 6,535. 65,535, same thing. I think it's really handy to use these hex values because sometimes the numbers you're going to have to work with are not as convenient as that. So that's our first value. And then, I've got 16 more bits to work with. And I know that the max neighbors per cell is 15, which is actually very conveniently OXF. That's 4 bits. 4 bits times 4 values, neighbors, index x, index y, index z, well, that's another 16 bits. But OXF is sitting where I want to store my distance value. So I got to move that over, which is really easy to do with a couple of double less than operators. I want to move those bits over, shift those bits over 16 values, and now I've got my 4 bits right here. And now you're thinking, okay, but I got to combine these values together to pack them together, right, before we send everything out. So all we have to do to pack everything together, assuming the starting bits are 0, is an OR equals. So a pipe equals is OR equals OX FFF. And now I've got all of that stuff packed together, but they're not colliding with each other, which is really, really handy. So then we need to unpack these values, which is a little trickier because I need this value, these 4 bits in the right spot, right? So instead of that, what I can do is say value equals, actually we want to go value equals, oh, right, I can just shift that over. So value equals value shifted over 16 places, right? Super easy. So that's the, I've taken my 4 bits from 16 to 20, and I've shifted them over 16, but I also need to mask them out because I'm going to have bits on either side of this that aren't going to play nicely with that. So then I just do an and equals OXF. I want to bracket this in parentheses because I'm always nervous about that. Very liberal with parentheses. So I'm going to mask out. I'm going to say everything on either side of this that's not up to 15, I want to mask it out, and then I can shift it over. So just in case I had something at, say, value equals OXF shifted over 20, right? So I don't have any of these values in the wrong spot. Cool. All right. So that's kind of the basics of how that works. It's a lot to recreate, but I whipped up some shader code that I can include in both Niagara and materials. I should post this on the EDC article that you're going to link to at the end of the show. Give me like an hour and I'll take care of that. So then in the avoidance stage that we've got down here, right, I already have most of the values that I need, right? Index X, Y, Z, and the neighbor count. And then for the sake of time, I'm going to skip over the quantizing the distance, but we can talk about that later. And this is, again, going out as a float value, so then I can just say set dynamic material parameter 1, and then I'm going to use the convert node here because I'm a huge fan of it. So we've got that value coming in. I've got my parameter. That's going to go into the X value. Then I'm going to make another float just so we can zero out everything else. So now I'm taking all of that information that I've got, and I'm sending it to the particles material through the dynamic material parameter channel. And then we can jump back to our particle material over here. And let's just, for the sake of time, I'm going to say, let's grab the dynamic material parameter, and then I know that this is up to 15. And actually, I have already staged for myself a helper function to get the parameters of the sprite. So it's just doing masking and shifting, nothing you haven't seen already. So that gives me my neighbor value, and I know that that neighbor value can go up to 15. And now what I can do is scale the brightness of the particle based on the number of neighbors, right? Maybe I want to have everybody be glowing more the closer they get to each other, but oh, they're running away from each other, and isn't that so sad? And then, yeah, let's go take a look at that. So all of these particles have maybe a few more neighbors than we're expecting, but we can also, as a fun little demo, we can also grab the grid index, right? So that's a float 3 value, and I'm just going to, for the sake of argument, debug float 3 values and send that out. I'm going to add that into emissive so that we can always see that. Okay. Apply and save. And then if this doesn't work, then what I know is that my references were messed up, which they were. Easy. So let's jump back into the particle system because I did get a little bit of time back. Go into the system, grab the sprite renderer, realize that that's in the wrong folder, go back to the main folder, grab the sprite material, plug it in. There we go. All right. So now we can play an editor. Ooh, and then the other reference was messed up. Live demos, right? Oh, that's the right one. Interesting. So I think that's because based on the grid size and all of that fun stuff, trust me, it works. Because that's how all of this stuff is working. I can prove to you that this works. So the health value, that's in the first 16 bits. I also store, if the unit is selected, that's 1 bit. That's the 32nd bit. And then the animation state, so if I'm idle or if I'm moving, the direction that I'm moving, and I use all of that. I use some of that in the particle system to select which sprite sheet in the flipbook we should be using, and then some of those values then get passed on to the material so that I can draw the unit outlines and all that fun stuff. So cool. It's, again, this is, in my mind, more about being efficient about your channels of data necessarily than the memory, but I think it's a fun trick to keep in your tool belt. So yeah, right, colors are just numbers, and numbers are just bits, and bits can be shifted and operated bitwise, as opposed to, like, you don't have to treat it as an array of 32 floats. You can just treat the thing as itself. All right, so we have arrived at the final little trick that I want to show you today. So let's talk about distance fields. Right, distance fields are basically for any given point in the field, the value at that point is the distance to the nearest surface. And if you've got a signed distance field, the numbers can be positive or negative, where negative numbers denote that you are inside of a surface, and positive numbers represent you being outside of the surface. And we'll use these to make a sort of pseudo screen space mask around our particles. So I did set up a couple of little helpers here. So right, we've got our positions render target. I've already got another render target set up in the material. That's just a 32-bit float render target. And we've got a couple of materials we're going to work with. So we're going to do this in 2 stages. The first thing we're going to do is use the draw material to render target node to create the distance field as that render target. And then in a different material, we're going to sample that render target by transforming its, the world positions into something that makes sense for that distance field. So basically, 2 steps. First, draw to the distance field, and then sample the distance field. So in the blueprint, this part is really, really simple, and I've already set it up for us. Every frame, we're going to draw material to render target. And now here's the thing about this is when we do this draw material to render target, that renderer doesn't know anything about the world of the main view that you're rendering. It only knows I'm rendering this material to this quad, and that's it. So it doesn't know the camera vector. It doesn't know world position of the thing that you might be sampling it from. So we have to transform the 0 to 1 values of that quad into something that makes sense for our distance field renderer. So what I'm doing on this plane that we're using for the fog of world is I'm sending in the center of the bounds and the extents, and that's what we're going to use to transform our values from 0 to 1 into world space relative to our object here. So here is ignore that, because I knew I was going to start running out of time here. So all I'm taking is our 0 to 1 values, shifting that over a little constant bias scale, scaling it out by the extents of our plane, and then adding in the center. So wherever the center is, we want to move that over. So now if we've got something that's 1,000 by 1,000, the bottom left corner is like -500, -500. The top right corner is 500, 500. And that way, so that's our UV value, if you will. I'm also bringing in the particle positions render target and its texture size. And then over here, because again, this is going to be a lot to type out, I should also put this snippet in the EDC article. So basically we're saying, all right, if I want to sample from the positions render target the exact value, and I don't want to worry about any kind of bilinear filtering, I need to offset my UV ever so slightly for that sample. And then I just initialize some values. I initialize the result. So the maximum value that I would expect to see here is 1. And then I'm going to loop over all of the pixels in the render target, X and Y. And then I get the UV that I should be sampling the position from, which then gives me the XY position of the particle in world space. And then the UV values that we're working with are also in world space. And what we can do to create the sphere distance field, right? I'm just going to use a circle right now. That is just distance between our 2 positions, in UV sample position, minus the radius of the circle that we're working with. And then because I didn't want to deal with numbers that are too high, go back, there we go. I didn't want to deal with numbers that are too high. I'm also going to normalize that to the hit radius. So this is going to give us 1 particle, and we want to combine all of these particles together as we are working. So all we have to do for that is say, just get the minimum value of everything. So result equals min result, and then our new distance field calculation. And then hopefully that compiles. Capitalization gets me every time. There we go. Oh, and another extra parenthesis. I told you I was liberal with parentheses. So we can apply that value, and this is going to draw into our render target. And then actually very conveniently, because of the way that I have contrived this example, we don't actually have to do anything super special for sampling our distance field, because I'm using the bounds of the plane that I'm drawing from to go from 0 to 1 to world space, which means that the distance field is already in 0 to 1 for the thing that I'm sampling it from, which makes this example really, really simple. So all I have to do is remember to set this to linear color, and then pass that out to the opacity mask, and this should mask out the areas around our particles. Okay? There we go. Aha! So we've got all of our particles looping together. They should be all looping together. That's fine. We're just going to drag everything in instead. How do you like that? There we go. P. I wonder why that's not working. Well, in any case, that's also how I'm doing the fog of war. We loved live demos. So yeah, again, this is kind of the same thing that I was showing earlier, and EDC article will have the more correct examples of this. But all of the particle positions are getting written into the distance field, which is our, which we're then using to render the fog of war. And then I just do like a couple of like dithering tricks to do that added effect, right? So we can move everything over there, and there we go. So cool. Actually, didn't go over time on this, right? So I think distance fields are a really powerful trick, and you can do your own things with these distance fields. It is a super deep rabbit hole. If you have ever seen Inigo Quilez's tweets or work, you might start to get an idea of how deep this rabbit hole really goes. I will also call out that there's a bunch of distance field in that example that's not visible on screen because, you know, I've got this giant plane, but we can only see this little part of it, and I will leave it as an exercise to the reader of how we can do that a little bit more efficiently. But right, all we're doing is transforming 0 to 1 in our UV space into the space that we want to draw our distance field in, so that we can then pull in the world positions of our particles, our distance field shapes, or whatever, we can bring those in. And if you want to get really advanced, when we're writing our positions to that render target, what if we also wrote like parameters of our distance field shape into the alpha value of that render target, right? I don't want to have to sample 2 render targets to get all these parameters. I can be efficient about my data channel use, right? So I'm sure you're a little curious about the results. So in the project that I've got, the way I have it set up, I can interact with about 4,000 units before things start to get challenging on a Galaxy S10. And most of that actually is from the distance field rendering, so I will leave it, again, as an exercise to the reader on how we can improve that in the future. Jump flooding. If anybody wants to come check it out or talk more about this, again, I guarantee you I will be in the Dev Hub from like 1:30 to 3 tomorrow, but there's also a TV screen with my schedule on it, so you can check that out as well. Okay, so what have we learned today? Well, we learned how we should be building real-time strategy games, and we also learned how we shouldn't, but instead, we learned how we can use Niagara as a compute shader to allow deeper interactions with our particles, how to use the neighbor grid 3D to allow our particles to interact with each other, and then we learned how we can pack a bunch of data into a single float with bitwise operators, and finally, we learned how to make a simple distance field representation of our particles, and I just remembered why that demo didn't work. So thank you all very much. If you give me 2 seconds, I'm going to go figure out how that works, and then we can get to questions. And this QR code will take you to my link tree, and I think one of the top links there is going to be the EDC article that I mentioned, and that has like a bunch of reference material that I used to prepare for this talk. Some of it's going to look really familiar. And of course, definitely check out the advanced Niagara content examples. That project is amazing. So cool. Any questions? Anybody know what I did wrong? Because we got 5 minutes. So I will tell you what I did wrong. The thing that I always forget to do when I'm doing this demo is when I make them module, I don't then update the input variables to the right things. So the reason that the distance field didn't work is I didn't set up the finalized particles properly. So that's a fun little thing with Niagara. I promise you everything will work. And if you'll give me a second, I'll actually get it working. Do it. All right, so we don't need to do that. We need this, we need that. Oh, I didn't even set up the inputs on that? Why did it set? Oh, ooh, even worse. I didn't plug in. I'm human, I promise. All right, so then we can go to the finalized units. Yeah, there it is, there it is. We're gonna do out positions, lovely, and then render target, lovely. And then we should be able to play an editor, right? And then we do my little console variable. Aha! We got it working. All right. So cool. Yeah, so like I've got all my little particles bouncing around, right? And like I said, the you know, we're wasting some of our time rendering the parts of the distance field that aren't visible on screen. If you want to get really deep into matrix math, you can create a transform space centered on the top left of the screen, so you can get a 0 to 1 value that directly maps to the screen. And then if you want to get really advanced, you can do a pseudo volume texture to give you a depth distance field, a pseudo, you know, a full volume distance field forward from the camera, fit perfectly to the frustum. We'll talk about that later. But if anybody has any questions, we've got a microphone up here, and I've got 3 minutes. Otherwise, I'll let you guys get on with your day. So cool. Thanks, everybody. Oh, Adi's got a question.
Hi, everyone. Welcome. Thanks for staying with us to the end of the day. This is Converting Blueprints the Right Way. Today we're going to show our approach that we took to make our own conversion tool for nativizing blueprints. We'll share a link at the end for more info. But basically, we're going to try and make this as entertaining as possible because this is basically the cup holders of game development. Like, no one wants to deal with this, but when they're bad, it's really bad. So let's find out who we are real quick.
Hey folks, I'm Eugene Chukharov. I am a senior SD rendering specialist at Amazon Games and currently working on an unannounced UE5 project.
That's right, I'm Anthony Vaughn, lead tools engineer at Toys for Bob, and we also are working on an unannounced Unreal Engine 5 project. So let's break down the problem, like why we're here at the best talk at Unreal Fest. So here you have the problem, right? Your humble data-only BP, right? Starts out, innocently enough, and oh look, you add some variables and some functions, adorable. And then all of a sudden, it's bam, spaghetti-geddon, right? It's go time and you're hosed. You need a savior. You know who to call, but okay, maybe not him exactly, but you need something strongly related to him, right? C++ or Verse, and we'll get into options in a second. So let's break it down. So the problem we're talking about today is not a novel one, okay? All teams, big and small, deal with this, okay, at some point.
Now, scripters, they need to be nimble. And engineers, they need it to be performant. So perf isn't done until it's absolutely needed.
That's right, and everyone thinks, that's just the way it is. It's just, blueprint's gonna blueprint, right? Hooey. We're sick of it, we're decided to take a stand, and we're sharing our plan with you guys. So let's dig in a little bit further.
Now, before we do, who here has had to convert blueprints for performance reasons?
Show of hands, show of hands.
Pretty much
Wow.
everyone.
All right, so we're going to go with 99.9%, okay, all right?
How about complexity reasons? Yeah,
A little less, yeah, 75% maybe?
How about just to refactor it?
Okay, the entire audience, all right. Well, you're in the right spot, all right? So again, your BP has become too slow or too complex to manage, right? You have hit big O of MG time, right? It's tough. So it's time to convert them.
Now, BPs are exclusive checkout. And you are using source control, right? Because if you're not, there's the door.
Ooh, it's harsh.
No,
Harsh.
hard references are everywhere. It takes lots of time to find them.
That's right. And you can't block scripters for any meaningful amount of time during this process.
And you can't move it on to C++, because then engineers will become a huge bottleneck.
That's right. Then scripters revolt, and producers will freak out from the burn rate.
So what type of conversion do we need? Well, let's talk engineers. They need time to get to it when they can, and as little time pressure as possible when they do.
That's right. Designers, again, like I said before, they can't be locked out of their BPs, okay? And not only do they need to be able to stay working in their BPs, they need to be able to extend and refactor them along the way during conversion.
Exactly. As for QA, well, they shouldn't be able to tell the difference that any implementation change ever occurred.
That's right.
So what are the steps that we're after? So here's a typical BP on a typical UE project, right?
Sure. Let's just say yes.
So Eng needs to come in. They need to lock a ton of assets, including BPs, maps, sometimes INI files.
And design is blocked now, right?
And Eng is stuck for a long time doing something they don't even want to be doing in the first place.
That's right. And we're talking days to months, which does sound dramatic, but that's not a joke. Like BP conversion, depending on even a minor complexity, which we're going to demo to you in a second, gets long and fast. It's rough.
Yeah, and meanwhile, the team keeps moving and adding more BPs to the pile.
That's right. Missing out on the Playbox Switch 3000 launch, and now your producer has now gone fully into the red. They're burned down charting everything to the ground.
So, all right, let's break down what we need to convert. And it's basically these three assets, right? Your enums, structs, and blueprints. For enums, pretty easy. Create a C++ type, make sure it has the same amount of enumerators, and you're good to go. For structs, it goes up a notch. Same thing, C++ type, but now we also need to do a depth-first replacement because of all the dependencies. And for blueprints, even worse.
Yes, the same, but worse. Yeah.
And you might be thinking, no duh, Captain Obvious. you might really be thinking, what about redirects? Well, we constantly get asked, why not use them? And it's legit, but redirects only work in 3 situations. Native to native, which is what they're designed for.
Yep.
Enum replacement, and wholesale BP class replacement. And that's it. For anything outside of those cases, you cannot use them. They will not work.
That's right. So at this point, we saw the road ahead of us. We took a step back and we thought about like, sweet baby Jesus, is there anybody else who's made a tool for this already? We don't want to do this. And so here's what we found, okay? UE, they had a built-in nativization that tried to do too much behind the scenes, though. They went all the way down to the node level. It's not something we were interested in. Plus, anyway, it went end of life in 427, so it's not even an option even if we wanted it to be. UE's header tool is great, but that isn't meant for compilation. In fact, it can give you emit illegal C++ code. But again, it's not meant for that. It's just meant to give you a general idea of what your BP might look like. Other solutions, many solutions, abandon BP altogether. But this is the lingua franca of UE. We didn't want to abandon that. So didn't want to deal with custom languages. Many more required a modified engine. Now, listen, you're already in Epic's release cycle, your own team's release cycle. When you've inevitably modified the engine when you're getting close to ship, the last thing you want is another thing to try and coordinate. It's just too complex, too many options. And then we even tried to throw large language models at it. Large language models, obviously the name of the game at the show, and they are coming along extremely well. This is still a little too much of a nuanced process and too customizable. It's too bespoke for each team. It became a manual process with even more steps. So it was just compounding the problem, not helping it. And none of them did the hard parts. And that's what we're here talking about today. Reference fix-up, post-processing, all that jazz. So you need a tool. That's again, why we're here, and we want to share a lot of pitfalls that we found. No one else is providing a good automated solution.
So before we set out, we set a few requirements for ourselves. First one is that we want a single senior engineer for about an hour. The project must stay in a runnable state throughout, and all assets and the references must be updated. That includes all maps, all BPs, and all the INI files. Source control should also be automatically updated, and everyone should be back to doing what they want to do. Engineering is code, design is scripting, and BPs can be converted repeatedly, all with no engine modifications, resulting in big cost savings and morale improvements. Producers are happy, we're happy.
That's right. That's right. So we're going to do the best idea pot.
One more slide.
Oh, we got one more slide? Oh, yeah.
All right,
oh,
demo
yeah.
time. Let's check it out.
Demo time. We're going to be doing the unthinkable and demoing live. Nothing is going to go wrong. So let's switch over to the old laptop. Yeah, for doing right. Pretty awesome. All right. So, in our fictional dev team, we decided that our designers thought the Lyra project just wasn't cool enough, and they needed doors. You know what? Doors would make a game. Now, the reason why we also chose this is because we were able to make a full BP door system that's purely in BP. So let's just say they're like, engineers, don't worry, sit back, we got this. We're doing a full BP situation for you. The doors are very, very complex. So let's just take a quick peek.
And Anthony, I'd like a high score on this one.
Yeah. I don't want to detract with my awesome FPS skills or third-person skills, so I'm just going to show the doors in action. But yeah, so there you go, doors in Lyra, who knew? And again, we'll show you an example in a second, but they did a pretty big system with this, right? So let's show the graph. Let's show the BP first.
Check out the BP first. Yeah, so let's start from the top right? It's an actor parent class, as you would expect. On the left here, all the components that make up this door. And if we go to the viewport, surprise, surprise, it's a door. If we look on the left side there, these are all the functions our designers put together to make sure our doors function the way they should. And if we go to the event graph, they also created a few component-bound events to handle overlaps for player collision.
Yeah, not half bad.
Pretty basic.
Pretty basic. So I'll bring up the graph, right?
Let's do it.
So we called our tool for this demo the Convertomatic.
Trademark?
Yeah.
Not really.
No one has ever thought of that name before, which is great.
Now, you might be looking at this and you're thinking, that looks a lot like the reference viewer. Sort of. if we look at the reference viewer, this has a lot more stuff in it. The reason is that because it shows you every asset it's referencing and every asset that's referencing.
Right.
All we care about is what types does our class depend on in code. So we grab up all of those and bring them over during the conversion process as well. So now Anthony, all he has to do is select them all, pick a folder, and we have a very convenient doors folder, and hit convert.
So practiced. So this is going to take a second. So we're going to talk to you about the 7 discrete steps that this is going through, right? So first of all, you're rounding up all your references. Everything, when we right-click that BP door, what does it reference and what does it contain? Those are the types that you're seeing in the graph, so dependency gathering. Then build your context data for each of those. You're going to have to rebuild them and reconstruct them natively, so you need that. Then you're going to emit C++. In our case, you could be emitting something else. We'll talk about that in a second, too. And then compile so that Kismet and the reflection system are now aware of your new types. Then for BPs, you're reparenting. We'll talk about why not replace, and we'll talk about that in a second, too. For some data types, you're going to do a wholesale replacement, which is going to feel good, cleansing. And then we're going to do the real tough nut, which is post-processing, like we mentioned, reference updates. Gosh, everything. It's going to be amazing. And then not just for the internal types, but also for this as well. Oh, no
Anthony,
way.
you broke it.
What did I do?
Did you delete the alt files?
Oh, did I not?
I don't know. Let's check it out.
Let's check it out real quick. Please hold. I'm going to say, you know what we're going to do? We're going to kill that. Then we're going to go to doors. And then trash those. And then we'll fire that up. What demo wouldn't be perfect without a perfect failure? So let's fire that back up. But yeah, so again, the point for doing all this, though, is that each of these steps along the way, Kismet is going to be trying to help you, as Kismet does. So you're going to find out that a lot of our advice is going to really revolve around making sure that you kind of are a good citizen to Kismet after the fact, I think.
Exactly.
Oh, you know what we should do is we can just throw the video up.
That's right.
We have a backup video. That's fine. Actually, let's go ahead and do that. I think it's going to be better. And what we can do is go back to the PC. And let's see. Boom. Yes. All right.
And our designers decided that.
Oh, yes, we got audio too.
Amazing. Too far.
Too far?
Yeah, much better. All right. There's
Too far.
our doors.
Okay.
Honestly, do now because
The
Perfect.
Yeah, there it is.
this makes sure this gets rid of hard references everywhere. It also makes sure to preserve all your default values and the values that you set within the level instances as well.
Yep, that's right. And that's the hard part. That's why we're talking to you today. Again, people get so focused on a very small part of this, and honestly, this is the gnarly stuff. All right, it succeeded.
Imagine that really happened.
Now we can walk you through what each of these sections mean.
All right, let's take a look at this first section. So this, as it says there, are all the types, the blueprints that were converted to C++, and then reparented to their new parent class, as you can see right there. We also show you what the new C++ parent is. And then in the next section, these are all of the assets and levels that used to reference the blueprints that you just saw in the previous section that now point directly to their newly converted types in C++.
Right.
So removing all hard references to those types.
Honestly, do it now. We've all been there. We all live when those hard references get made. VPs get duped, and your project loads slowly, and more slowly all the time.
Absolutely. And in this section, well, this is everything you can delete right now.
Yeah.
And in your tool, you can add a button here to delete these right away if you're you trust your designers. We recommend doing it manually. Don't be safe.
Yeah, exactly. We tend to not do destructive stuff in tooling unless really possible, but hey, at least now you know you have the option. Okay. Should we fire up the BP and check it out?
Let's make sure the game still runs exactly as it did before.
Oh, yeah. Valid point. Valid point. This is why there's 2 of us on this project and not just one.
I think you're inside a wall, Anthony.
Oh yeah, I forgot about this.
I like to do that. Let me. Ha! I am. Sorry, guys. Please hold.
So our backup also had a glitch. in it. This is live development, folks.
We're doing great.
Yeah.
All right. Bam. Much better. All right. There's our doors from the first half of the demo. Do they work? They work. Oh, wow.
Hey,
Yeah. So again, that's proof is in the pudding, so to speak.
awesome.
All right. So now we can look at the BP once again.
And like before, let's check out the parent class in the top right. Look at that. Now, it's the native base store class that we emitted into code. And if you look at the left side where all the components are, these are all now C++ components. And if we look at the viewport, exactly as you would expect, all of the defaults were preserved. This is still a door.
Hooray!
Now, if you look at the functions, you'll notice they now all have a suffix of _deprecated. The reason this is, A, this signals to designers that these functions should no longer be used directly and that they are being moved to C++, but B, this allows us to preserve functionality while engineering puts in the new implementation in C++.
Right.
And I'll show you the details of that in a moment.
Yeah, that's a critical requirement that we highly recommend you adhere to.
Absolutely. Same thing with these events here that are component bounded edits. As you can see, they are suffixed with _deprecated and do the exact same thing under the hood. And then Anthony, if you don't mind searching for interact,
Oh yeah, that's right.
we'll highlight a really cool thing. So check out this cast. This used to cast to W_interact. This now casts to the interact C++ parent class instead. And Anthony, if you click that little set node right there,
Yeah.
you'll notice this variable type as well is now using the C++ type, which is a little hidden if you expand that detail frame just a little bit.
Yeah. Sorry.
Perfect. You see that is the C++ version of this class.
Yep.
We should have recorded the whole
Yep.
thing.
Key. And again, we're going to go in a much deeper dive on the benefits you get with CAS and which you're able to do now at this very moment that the native and BP are in perfect sync. All right, let's check out the code. What do you say?
Let's do it.
All right. So what do you say we do let's do an enum that's kind of simple first.
Door security should be a good one.
Yeah, perfect.
Nice.
Ah, damn.
I guess we forgot to fill out our copyright.
My
But
bad.
that's where your copyright would go.
Yeah, that's my fault. I will do that. I promise I will do that.
After that, it's your header boilerplate, right? Prime on ones. Any includes, in this case, we do core minimal as well to be safe. You can omit that if you like for enums. For the enum itself, as you can see, again, you enum to printf as you would expect, but then you'll notice there's a meta tag that is custom to our tool. You should have one that's custom to your tool, and we'll go over why that's important in a moment. And then, if you notice, all of these have comments. These used to be tooltips on each of the enumerators in the user-defined enum. We bring those over as comments above each one, so this way, you get them in the IDE as well as inside of UE, just like you did before.
Yep.
And Anthony, do you mind speaking about the disappointing?
Yeah, so in this, remember, critical core pillar of your tool should be to keep designers working in BPs as if, just as they were before this conversion started. One of that is maintaining their display names. They named something key/item. You'll also see question marks a lot in variables. We've seen it all. Obviously, those aren't valid C++ names, so we use display name to keep that translation for BP, and then give it a C++ safe name for ourselves. Let's crank it up a notch with structs.
Door safe.
Door safe. Yeah, that's the one.
So to start with, same as enum, nothing changed here. But now we have a ustruct again, our lovely meta tag that we added ourselves.
Yep.
And if we go down, you can take a look at our properties now. Oh, again, tooltips added as comments, your standard U property, edit anywhere blueprint read write for use properties. These will be different per blueprints depending on what the options were set by the designer. So we do respect those. Yep. And if you notice, every field has a safe default that it initializes to, following UE's spec for use structs.
Yeah, and you'll notice too that as Eugene touched on, very rarely do we just assume certain property specifiers or class specifiers need to be there, only unless it's extremely obvious. You have all this reflection data. It's right there. Just use it and just copy it over. It's not that bad.
Yep,
all right.
absolutely.
Now, obviously, the most complex thing is BP class, and it's not a replacement. Now it's a derivation. Let's talk about that.
Yep, that's right. So this one has a lot more includes to begin with, right? So these are all the types that it uses directly in this header. And if you look, we alphabetize them right out of the bat. You should do so as well, please.
Yeah, exactly.
We also do forward declares as opposed to including these headers. It's going to help with the compilation time. And frankly, it's the better way to do this anyway. And as before, we have our tooltip on top, the meta tag as you would expect. We do default to using blueprint type and blueprintable for our actors or UObject classes. The reason that's the case is because it's easier to be explicit and redundant here than parsing a actor or any of your base class chains and trying to figure this out.
Keyword being chains. It's too much of a headache. Just safe.
That's right. So now if you look at these functions here, this is what used to be in your blueprints, and they were getting called directly. Now all of your blueprints are calling these, and these, for the time being, are routing back to your blueprint logic.
Yeah.
And we'll look at that in just a second. And again, as Anthony noted previously, check out that display name. Is locked, question mark? Obviously can't have that, so, but we do want to have a consistent designer experience.
I'm Ron Burgundy? Yeah, exactly. So that's right. That consistent design experience is critical. Let's check out the components.
That's a lot of stuff that got converted.
It is. It's a ton. And Eugene just talked about this already, but again, it's all of this stuff is in the metadata. Respect it and carry it over.
Yes.
Right?
Yes. Our components. You can see right now they are simply just declarations of those components. We'll take a look at the construction of them in just a moment. And then Anthony, if you scroll down a little more, here's some view properties. And you'll notice that not only do we preserve the edit and blueprint read-write options that were selected, we also check if they are replicated. Do they have an on-rep, which this one does. Check that out.
Yeah.
We set that connection up as well. And we also preserve the defaults that were set in the blueprint, as you can see.
Yeah.
This way,
Yeah.
when you create child blueprints, you get a consistent experience from this base class.
That's right. And again, this isn't the quality of life stuff. This, you have to support this.
Yes.
You're making a multiplayer game, especially, well, you're dead in the water without it.
Absolutely.
I think that's it for the header file.
Yep.
Yeah, let's check out ye old CPP.
So here you can see we have the rest of our includes. Now, we are making the assumption here that you will be using these includes because it's a safe assumption. In your tool, if you would like to have your engineers add these as they need, by all means, you can do that.
Yep.
In the constructor here, you'll notice we recreate the entire component hierarchy as it was in blueprints, including any attachments and sockets and offsets that they had within your blueprint.
That's right. And we also, again, it's kind of a small point, but it's a critical one. Where there's a constant declaration for a certain type, use it. One of our kind of, I don't know, thorns in our sides or requirements, lowercase r, was this stuff should look like what a human would write, what an engineer would want to write. And it should also respect your team's coding standards. We come from places where, yeah, if you have an identity quaternion constant, then use it. Don't emit the equivalent as the unrolled version. Same thing with one vector. if it is a one vector, use the constant available to you.
Yeah, and to add to that point that Anthony just said of outputting code that an engineer would write, that was a tenet for our tool here. That was a very strong driving point for the way we built this tool. So if you look at also 5T5 and 56, you'll notice those component boundaries that we looked at just momentarily, we bind those directly in the constructor to the new C++ class functions. Because, well, why not? You can do that directly right here, right now.
Yep. So let's take a look at our favorite on-begin overlap, good old interact back.
So this is how we
This is
make
the cool
sure,
part.
Your blueprint, while your project stays in a working state during the conversion process. What happens is all of the calls that used to go directly to your blueprint logic now are routed through the C++ function, which for now simply routes back to the deprecated blueprint logic that is still in your blueprint. And then when an engineer is ready, they can come in here, either add the new implementation right here if it's a one-to-one conversion, and then comment out the line below. Or if you say you want to do a re-architecture, you can simply use this as your source of truth for everything in your project and start re-architecting
That's right.
this class any way you want.
That's right. Anecdotally, we've heard consistently that a lot of, your lead engineers, your tech directors are like, well, obviously I'm not going to want necessarily, probably not, a one-to-one carryover from this one-to-one function reimplementation. I've got a larger re-architecture going on. Fine. But you must keep your designers able to work when they can. So we've got at least, if nothing else, they're still working, which I think is more important to keep everyone unlocked and going. But also, you've got right here a very clear list and a very clear touch point of where to make your changes.
And also, the other super cool thing you can do with this tool is now you can also auto-generate CVARs to enable or to swap between the old deprecated blueprint logic and the new C++ implementation at will, allowing designers and QA to test for regressions and any behavior changes.
Yep.
Super easy, super quick.
Yep, exactly. Yeah, I should have said regression testing, but any testing you want. But yeah, that's the key. So this is sort of the flow state that you want to keep in yours. So with that in mind, I think that concludes the demo. And
Anthony, I just noticed it. Would you like to speak about that duplicate?
Oh yeah. Okay. Line 167 and 169. This is interesting. So it's an edge case you're going to have to handle. Even though we said code emission isn't the hardest part of this, and it's not by far. Okay, we didn't. That's a little bit, but there are some edge cases and some theories things that you need to handle. One of them is variable shadowing. C++ is more strict than BP script, and so this has this shadowed. We detected that is loading shadowed a previous variable or function declaration. So we have a system in place which just does index duplicating. So they're guaranteed to be unique, and you can just sort of automate that. It's a pretty straightforward thing to automate, but you got to take care of it. And while I'm on the topic, remember, someone can name a variable in BP that's nothing but C++ illegal characters, 100%. So
Evil.
Yeah. I'm not saying that's great, but you have to take into account for sure.
And just to quickly note as well, using display names, your designers will not see that at all. They will see the previous parameter name like they did before.
That's right. Because let's be honest, this process is talking about, you're trying to take power away from us or whatever. No, everything will be as it was before. Yep. Even gnarly, horribly named variables in BP. So, all right, that concludes our demo. Let's get back to it.
Let's do it.
Okay, so imagine that was us right now.
And before you go on, Anthony, real quick, I should have said this when the video was up, but if you're passing parameters such as f vectors or f transforms in blueprints, they default to doing a copy. What you can do is be smart about it and catch those turn them into const drafts right away.
Yeah.
But to keep the experience consistent for designers and blueprints, use the auto-create ref term to keep the default value pin exactly the way it was. Very useful.
Yeah, and when this video is posted, you can pause and see the auto-create ref term meta tag that we use in our output. But yeah, good call. So regardless of what your specific needs are, you should break your tool into 7 discrete parts, OK? Dependency scan for this is, again, gather up everything that needs to be converted. Asset-specific context data, build that data model, right? Code builder, you have the context, you have everything you need to know to create a native class. Make that native class, or classes, frankly. And then do a code recompile. We're going to talk about a couple options there, but live code is your friend here. Post-process, the chunky, the reason we're here, really. Update all those references, fix all those cast nodes, go deep every pin upon pin upon pin. Reference updater, do the same thing for everybody else in the world that's looking at these things you just changed. And finally, restore pin links. And we'll talk about why we call that out as a separate step in a second.
All right, let's dive into dependency scan. So the goal of this phase is to, like I said in the demo, gather up every type we need to bring along with the type you want to put to C++. So let's use this asset as an example, as a starting point. First, we need to discover all the types that it references, and all the types that reference it. And then you're going to want to rely on the UE's reflection system for this. Run through the uClass, uStruct, uenum, you name it. Go through it.
It's everything. So let's start with user-defined enums. You're going to see a pattern here that enums are going to be the simplest problem case, right? They can't reference other types. So there you go. Basically calculate their class name and prefix, round them up, gather up any modules that depend on them and packages that depend on them, and round it up for source control.
With user-defined struct, complexity goes up a notch. These can grow significantly, since struct variables can contain blueprint types as well as other struct types. And you also need to check, is it a row data struct for a data table? Use the asset registry.
Yeah, that's not in metadata.
No.
So BP interfaces, about the same complexity as structs, but for different reasons. Obviously, they have function parameters. So you can treat their function parameters as properties. You're going to have to write some code to handle U properties. Fun fact, parameters of functions are literally stored as U properties of U function data. So that's kind of nice.
Thank goodness.
Silver lining.
So blueprints, well, they're the culmination of the other two. The reason is because they contain all the possible elements we can convert, as you can see in the snapshot from the demo we just did. Now, off the bat, you can ignore the construction script. This is only for blueprints. And we'll come back to the functions and variables used within it in the later step in the process. Anim graphs, you can ignore those as well. They are meant to be put together in NMVPs, not code. And just like the construction script, we'll come back to the functions and variables in a later step.
That's right. So now we know what has to be converted. We've got all the information. Let's build that context data, OK? These are the elements you need to worry about. That's all you need to care about. Type info, variables, functions, events, event dispatchers, and components, right? Again, enums are the simplest. They only have type info. You can get everything you need from it. One kind of catch-all is UE stores enumerators as new enumerator 0, 1, 2, 3. You've probably seen this if you've ever emitted a BP before. That's safe and consistent, but it's ugly if a human were to write that. They wouldn't write that. So you can dip into the metadata, the type metadata, to get the pretty enumerator names and as well. And you can use it to ensure that you get a safe type name as well. Remember, BP allows C++ illegal characters. By the way, making sure type names and variable names and all this stuff are type safe is going to apply to everything that we're going to show next. So this is the last time we're going to mention it explicitly, but make sure that this is part of the lifeblood of this whole tool, frankly. Yep. Structs take it up a notch with variable support, right? For type info, they can be used as potentially used as data table structs, right? And again, as we mentioned, no type information will tell you that. The asset registry is your friend there, right? Variables, properties for structs is a much bigger topic. We're going to get to that in a second. Interfaces, again, same thing, but for different reasons because of their parameters, their parameter lists. There are also bigger topics, however, because of that. So we're going to get to them in a few slides as well.
And blueprints, they have all of them and then some.
And that's why you're talking about it.
Thanks, man. So let's talk about class specifiers, because they require a little bit of a special attention. You can add these right off the bat, like I said earlier, and you can capture the rest of it from the reflection data. Don't add deprecated. If you already marked a blueprint deprecated, you obviously don't want to immediately deprecate the parent class. Doesn't make sense.
Self-esteem issues, maybe, I don't know.
You should preserve the hidden categories UClass specifier. They're very helpful to clean up the details panel. These often, the category and display names, they often show up in the metadata. You would never write that yourself. You put them directly on the UClass specifier. You probably need to move them over. For variables, let's start with what we can ignore. The generated default tuner component, if it exists, it'll show up as a U property. It'll get in the way. Just ignore it. For Uber graph frame properties, same thing. They have runtime and BP only. Widgets not marked as variables, they only live in the widget tree. Don't care.
Feels good.
For never replicated variables, you need to grab the rep notify func name, and obviously keep a mapping between the two, but you're going to have to do that in code afterwards.
That's right.
There's a lot to go into here, but you can check out the rest on our site. But quick note on this. This is a fantastic chance to convert hard refs into soft object pointers and soft class pointers right away, as a batch. Quick, easy, just do it.
Yep. Everyone will love you when your levels load more quickly in the editor.
The goal with this one is we basically just need to capture the function signatures. For custom events, they simply live on that node. Just go in there. It'll be the U function that they generate. For component bound events, you also need to store what component they belong to, obviously, for that mapping in the constructor. For function signatures, check the function entry node for this one. Now, for interface functions, if they have a return value, check the function entry node in the interface graph specifically.
Right.
And for those that don't have a return value, they'll be simply on the UQ2 node event itself. The parameter context data, just treat that as variables. Super simple.
Yep.
For components, the hierarchy is critical.
Yeah.
So for this one first, check if the root is defined in BP or if one needs to be made. It can be defined in BP or natively.
Right.
Always replace default tune root. Honestly, makes your lives easier.
Yeah.
Now, after all of this, you're going to want to save your pin links on every asset that you're touching or updating, because Kismet constantly tries to rebuild pin links, which normally, great, thank you. But we're doing so much behind Kismet's back, we need to preserve them ourselves for a later step.
And we're going to talk about that in a second. So now we have everything we need to emit code, right? We keep the code building step discrete for a couple specific reasons, right? First off, it's easier to support multiple languages, right? So chances are you're going to be emitting C++, but you could do verse, no problem, or sweet protobuf, and that's something that Eugene and I are specifically pretty excited about looking at next with our own tool. It's just awesome. Anyway. One thing feels obvious speaking to a bunch of engineers, but allow engineers to group declarations at the file level, whatever your native language supports with that. It's gonna make sense. You know, obviously you're gonna have some enums that go with a certain class, or maybe you're gonna have all of your UMG widgets separated out in a UI folder. Just let them do it. Also, really though, this is a good chance for you to be a good C++ and Unreal Engine citizen, right? You have a chance to enforce your team's coding standards. There may be people on your team who have strong, I'm sure there are, opinions about those standards. Just put them in now, then you're done forever. It's awesome. And also, this helps designers, a chance anyway, given the dialogue that you're going to have with them about this, is you can help them become better scripters as well. So now now emitted, let's compile it, all right? So the context data is built, we're good to go, but none of it is loaded yet. All right, you've got two options here, right? One is our beloved live code. It's been around a long time. It's easy to trigger with a single API call. It compiles, you see pass fail right away. It's instantaneous nearly, and it's a faster workflow. You're never leaving the editor, and therefore you're never leaving, you're not to save context state. The cons, Technically, you can't be 100% sure that your data is fully owned, fully formed, I apologize. But we found this just isn't an issue. Really, it's more of a lowercase c con than anything else. And so I don't know, whatever. But option 2, not that we're already giving you our opinion, is you can stop the process right there, exit the editor, save off state, and exit the editor, and then build again straight from your IDE. That will guarantee you, literally according to Hoyle, 100% that your data is up to date. But, and it's also cool too, one other pro is because you had to serialize all that context and all that state data, you've got it sitting in a file somewhere. You can look at it, you can pick it apart however you like. But again, that's more code chances for bugs to write out data. That's a larger surface area for you to mess up. It's also not a trivial thing to undergo. You have to maintain state across editor instances. Your team, I'm sure they have some custom tooling already that will interfere with that. So really, just don't do it. We recommend live coding. It's mature, it's stable, it's great.
Yep. So now we're on to the post process. So we have our native types. They're created, they're loaded, array. Let's make the VPs aware of them and use them. Now remember, it's these 14 assets from that demo.
That we totally did live.
Definitely. which in our conversion results is these 2 sections. For the enums instructs, we don't care about those. You can skip them during the post process. They get deleted. For blueprint classes and interfaces, this is where you need to focus. Well, now begins the hard part.
Yeah. This is where it gets scary. So there's 2 major sections to the post process, okay? Phase 1 is clean everything out, all right, from your BP data. Save off your BP and child blueprint class default objects. Remove variables and event dispatches from the BP. Same with implemented interfaces. Same with the simple construction script nodes and components, okay? Also, a weird one, rename the component archetype instances. It's not obvious why you would do this, but basically we rename them. They need to be around for Kismet to actually do some updating for you, but they need to be renamed so they don't conflict during the reparent process to the native version. It's just something we found out that wasn't obvious. You're aware of it now too. And then finally, reparent the BP to its native type and reinitialize it.
Yep. And for this one, if you remember no other section from this presentation, please remember this one.
Yeah, this is the meat.
So for attachments on instances, components of instance actors still refer to VP components. That would normally fix itself up when we restart the editor. But we recommend doing this immediately because otherwise your actor components won't show up properly in the level. To do this, you need to back up the class override before conversion.
Yep.
And if it was originally a BP class that you converted as part of this conversion, restore it to that BP instead of the new native type.
Right. Because
the implementation details are still there. If it was originally something else that a user set it to, obviously restore it to that value.
That's right. And then finally, fix up functions and custom event nodes. You have to fix these up. Fmember reference is your friend here. If you don't know it, you're going to know it really fast. Basically, for BP functions now need to implement the native deprecated version. Okay, so in BP, assign this to the native deprecated function. Excuse me, and you're going to call reconstruct node on that a lot.
And we mean a lot.
Yeah, yeah. We really got intimately familiar with that function. Clear out user-defined pins again because now the native function has defined those. Kismet will pick them up.
Yep.
Delete custom event nodes. Fully recreate them. So replace them with the regular event node and point it to the deprecated native version, okay? Rebuild your delegate nodes. This is another thing, and these are all the checklists you have to do for those. So if it's an event dispatcher that was converted, that we converted in the process, or you converted, you can then bind it in the C++ constructor. We just showed you that in the video. So we make sure to do that in our tool. You should too. And in BP, we can simply delete the bind node. Again, it's still there. It's still fully accessible. It's just easier to manage for those who are going to have to refactor it. With custom event nodes, you simply connect the red wire to your bind node, yeah? But if that custom event was converted, then we instead need to bind the converted C++ function, right? And to do that, we create a create delegate node that points to the converted C++ function. This is the only one that has a graphic with it, because that's hard as hell to visualize. And then you pass that into the bind node, okay?
Now, for rebuilding the component bound events, these are very similar to custom events. you simply delete the component bound event, then replace it with the UK2 node event instead. But this now points to the deprecated version of the original BP event.
Right.
You definitely need to go through, this is the fun part, actually, is replacing all the calls that were going to the blueprint functions with the native functions themselves. And again, fmember reference is where it's at. For this one as well, little tip, use UK2 node call function, set from function. Can anyone say function again?
Yeah, exactly. It's a lot of functions. So for get set variable nodes, you're going to have to update the member reference info to the new native type, as you saw with in our example. And also, by the way, in the UK2 node function entry node, local variables live here as well. We got to go.
We also need to fix up the archetype instances. So during reparenting, actor view properties that point to instance subobjects lose their values. In other words, a placed actor in a level with variables that refer to its own components get nulled out. For this, simply iterate over the archetype instances. Make sure you skip the CDO. It's, for some reason, included in that list. And one more. Yep. Assigning the subobject to the property it belongs to, pretty simple. Just keep a map beforehand and apply it after.
That's right.
And finally, the last step of post-processing. We update the TDO. So for this one, save off the property values, and then reparent, then restore those back. Your archetype instances, they'll get wiped as well. Make sure you keep track of those. And same thing for the child VP CDOs. Quick tip here, blueprint editor utils, get children of blueprint helpful.
That's right. So now we're in the second to last step, similar to post-process, but we're updating all the referencers, right? There's some important call-outs here. So these are for everything in BP that reference the things you converted, right? Cast nodes just became super easy. Before, they were hard references. Well, now you can cast them to the native type, which is free, safe, and you definitely want to use native parent, not the BP one. Now it's a simple pointer assignment. It's a soft reference. It's awesome. Use it.
Yep. Wildcard pins, well, they should be left to Kismet.
Yeah.
They're most commonly on macros, obviously. And for this one, there's so much type deduction that needs to happen. Easiest thing, just disconnect them all and reconnect them.
Yeah, ask us how we know.
Yeah, just let Kismet do the work.
Yep. OK, so now, so your enums require patch up. Early we showed you how you restored those enums with the indexing values. Make sure you remember you kept your mapping that dog and cat equal new enumerators 0 and 1, obviously.
For data tables, so they need a little bit of a special handling. The native type is identical, take advantage of that fact. So simply export the data to CSV, and then re-import it right back into the same assets, but this time with the native structs.
Yeah.
Done.
It's just easier that way. We tried the hard way, not great. So don't forget IRNI files, right? Basically, all you have to do is scan every class with the config flag set and check each property for a ref to a newly converted type. Honestly, we recommend stopping there for IRNI files. Let an engineer look at it from that point. You need to make decisions. It's not very straightforward to automate.
Yeah, it needs to be a conscious decision.
That's right. Now, basically, you're done. It's go time. All references are updated. Now it's time to do a Kismet compile, right? You will see some compilation errors here in Blueprint, but that's what this next step and the final step is all about fixing up.
All right, so this one, the conversion tool did a lot behind Kismet's back. So it Kismet removed pins. It kept orphan pins. It maintained the valid connections. Not great. I get it. It's just trying to help. I know. Yeah. But Epic, can we please have an option to turn this off? That's great.
We are a special case.
So for this, honestly, disconnect all the pins. A lot safer and easier that way. And then you can use the pin link data you saved when you put the context data to restore it back. Quick tip, combine split pins at save time. There's just less of a headache that way. And then split them again at restore time. Also, don't forget pins. They can have illegal C++ names. That bit us.
Yeah.
And so did this. They have default values. Make sure you restore those properly.
All right, so that's pretty much it. And we're coming up on time, so we're going to blow past this. But now you press play, you test, validate, submit. And just like our demo that went perfectly live, so will yours. Scripters are back in BP. Engineers are fixing things in code. It's great. And your producers aren't going absolutely nuclear, which is awesome.
But there's some cool stuff you can do now as well.
Yeah.
So we are allowing designers to iterate during conversion. That was a requirement for us. Here's some tips to make that work. So build the context data only for the newly added blueprint types. Remember that tag? Use that to detect it.
Yep.
Post-process and reference update don't change at all. The code building, you do need to figure out where to put the new code. Don't build a C++ parser. Keep it simple. And then, as if being able to reconvert infinitely wasn't awesome enough, you get a sort of a performance subclass factory as well.
Your designers might like this, yeah.
Yeah. So it's pretty straightforward. Let's say design made a BP enemy class, and then we converted it to a native class, A enemy. And they've reconverted it a bunch of times alongside engineers, thanks to your sick custom meta tag.
Sick. But then your creative director hired the best flying enemies designer on the planet, and you can tell by his hair. So they created the most awesome flying enemy, but started dumping it into the native class. So if you built your tool according to our steps, the conversion process will automatically reparent that to a new native class, maintaining the hierarchy, and then it's just a matter of duping the BP, switching it over, and starting fresh again. It's a huge knock-on thing we didn't even realize was going to happen.
Yep.
So.
And now we're thinking at the speed of thought.
Yeah, we are.
Designers, they can use it.
Got to deliver. And critical delivers will be performing as well before the 11th hour, which is fantastic. And
production loves it because the team is working together earlier on.
that's our time. Thank you guys so much.